Hello there, and welcome to Science for Sleep, where curiosity slows its breathing and science takes a gentle walk beneath the quietest parts of the night sky. Tonight, we are turning our attention upward, not in a hurry, not with a telescope pressed urgently to the eye, but with the kind of relaxed gaze that lets the stars take their time introducing themselves. Above us, stretched across the darkness like a familiar shape you might recognize even from a childhood memory, waits a figure that has travelled through centuries of human imagination. Orion, the hunter, standing patiently in the sky, carrying stories, distances, and sizes far greater than his simple outline suggests. Before we begin wandering through that vastness, let me ask you something small and human. Where are you listening from right now? Are you tucked into a quiet room, or maybe watching the glow of a city fade behind a window? And what time is it for you in your own little corner of this spinning planet, as Orion waits somewhere above, either rising, setting, or quietly drifting behind the daylight? If you find this gentle exploration soothing, or if it feels like a soft way to unwind after a long day, you might consider liking the video or subscribing. It helps this calm little space reach others who might need a moment of quiet too. Now, let your shoulders relax, let your breathing slow just a little, and allow your thoughts to drift upward, away from the ceiling and into the open sky. Because tonight, we are not just asking where Orion is, we're asking how big he truly is, not as a drawing of dots on a page, but as a real collection of stars scattered across an ocean of space so wide that even light takes years to cross it. Most of us first meet Orion as a shape. 3 stars in a neat line, a belt that feels almost intentional, like someone placed it there to guide our eyes. 2 bright points above for shoulders, 2 below for feet. It is one of the easiest patterns to find, even if you do not know many constellations. On a clear winter evening in the northern hemisphere, Orion rises confidently, as if he knows he's meant to be noticed. In the southern hemisphere, he appears flipped, standing on his head, but still just as bold, just as recognizable. At first glance, Orion seems simple. He fits comfortably inside a small patch of sky. You can point him out in a matter of seconds. You might even feel like you could hold him between your hands if you stretched your arms out toward the horizon. That sense of neatness, of containment, is one of the great tricks the night sky plays on us. Everything looks like it lives on a flat surface, like tiny lights pinned to a dark ceiling. But that ceiling, as it turns out, has depth, and Orion is not a single object painted onto it. He is a loose gathering of stars, each one floating at its own distance, separated by stretches of emptiness so large they make our usual ideas of size feel a little fragile. So let's begin by doing something simple. Imagine you're standing somewhere with a clear view of the sky. Maybe it is a field or a quiet beach, or a rooftop where the city lights soften just enough to let the stars peek through. You find Orion's belt, because almost everyone does. Those 3 stars in a row act like a signpost pointing your eyes outward into the shape. You trace the hunter from shoulder to foot, from one bright star to another. Your finger draws an outline that feels solid, like you're connecting real points in space. But here is where the story quietly changes. The line you're drawing is not connecting nearby neighbours. It is jumping across enormous gaps, from one star to another, that might be hundreds of light years closer or farther away. You're not tracing a single structure. You're stitching together a picture from stars that just happen to line up from your point of view on Earth. To get a sense of what that means, it helps to think about distance in a way that does not rely on numbers alone. When you look at Orion, the light entering your eyes left those stars years ago. For some of them, that journey began before you were born. For others, it started back when the world looked very different, when technology was younger, when the idea of watching a video on a glowing screen would have seemed like a piece of science fiction. Take Betelgeuse, the reddish star that marks Orion's shoulder. It sits roughly 600 to 700 light-years away. That means the light you see tonight began its journey toward Earth around the time when people were using early telescopes to map the heavens with ink and paper. Rigel, the bright blue star that marks Orion's foot, is even farther, about 860 light-years away. The three belt stars are scattered in between, each one at a slightly different distance, each one living its own separate life in space. So when you look at Orion, you are not seeing a single moment. You are seeing a layered view of time itself, a collection of pasts arriving together in your present. That alone stretches the idea of size. Orion is not just wide in space, he is deep in time. Now let us imagine something even more challenging. Instead of standing on Earth, picture yourself floating far away, somewhere else in the galaxy. Not just a little farther out, but hundreds of light-years to the side. From there, you turn and look back toward the region of space where Orion stars live. The neat shape you know so well would dissolve. The belt would no longer be a straight line. The shoulders and feet would scatter. What looked like a careful drawing would turn into a loose cloud of stars, each one separated from the others by distances that dwarf the size of entire solar systems. This is one of the quiet truths about constellations. They are not objects in space. They are viewpoints. They exist because we stand where we stand. Orion is a picture drawn by perspective, not by proximity. And yet, even when you strip away the illusion of the shape, something enormous remains. The region of space that contains Orion's brightest stars and its surrounding clouds stretches across hundreds of light-years. That is not a small neighbourhood. That is a vast section of our galaxy, filled with gas, dust, newborn stars, and ancient ones nearing the end of their lives. To put that into a more grounded frame, imagine light itself as a traveller. Light moves at about 300,000 kilometres per second. In 1 second, it can circle the Earth more than 7 times. In 1 minute, it can reach the Moon and come back. In 1 hour, it can cross the orbit of the Earth around the Sun. In 1 year, it travels nearly 10 trillion kilometres. That distance, a light-year, is our basic ruler for measuring the galaxy. Now imagine light trying to cross Orion's region. It does not take days. It does not take months. It takes centuries, hundreds of years of uninterrupted motion, just to go from one side of the hunter's territory to the other. But even that is only part of the story, because Orion is not just a scattering of bright stars. It is also home to one of the most active and visible stellar nurseries in the sky. Hanging from the belt like a small fuzzy patch you might notice even without a telescope is the Orion Nebula. This is a vast cloud of gas and dust where new stars are forming right now as you listen to these words. The Orion Nebula alone is about 24 light-years across. That means if you could somehow ride a beam of light from one edge of it to the other, you would be travelling for nearly a quarter of a century. Inside that cloud, gravity is slowly pulling material together, heating it, compressing it, until new stars ignite. These stars will shine for millions or even billions of years, long after the shape we call Orion has drifted into something unrecognizable. So when we ask how big Orion is, we are not just measuring a pattern. We are measuring a living region of the galaxy, one that spans space on a scale that makes our planet feel like a grain of sand on a long, quiet beach. At this point, it can be tempting to let the mind float off into abstraction, to think of Orion as simply huge and leave it there. But it is worth staying grounded for a moment, anchoring these ideas to something familiar. Picture our solar system. The Sun sits at the centre, and far out beyond the planets, past Pluto, past the icy objects of the Kuiper Belt, there is a distant boundary called the Oort cloud. This is a vast spherical halo of icy debris that marks the outer edge of the Sun's gravitational influence. Even that enormous structure, which may extend halfway to the nearest star, is only about 1 or 2 light-years across. Now compare that to Orion's region, which stretches for hundreds of light-years. You could fit the entire solar system, including its most distant reaches, inside Orion's space not once, not 1,000 times, but tens of thousands of times over. And yet, when you look up at the sky, Orion fits neatly between your outstretched hands. There is something quietly humbling about that. The universe is not just large. It is skilled at hiding its size behind small, gentle points of light. Let us linger for a moment on one of Orion's most famous stars, because it helps give shape to this vastness. Betelgeuse, the red supergiant, is not just far away. It is enormous in its own right. If you were to place Betelgeuse where our Sun is, its surface would extend beyond the orbit of Mars, possibly even brushing against Jupiter's path. It is a star so large that if it were hollow, you could fit the orbits of several planets inside it and still have room to drift. But even Betelgeuse, for all its size, is just one point in Orion's wide field. It is a giant standing in a landscape that makes even giants feel small. The stars of Orion are not standing still either. They are moving slowly but steadily, each one following its own path around the centre of the galaxy. Over tens of thousands of years, the shape of Orion will change. The belt will bend, the shoulders will drift. The hunter will lose his familiar outline. Humans in the distant future, if they are still looking up, will see a different pattern and perhaps tell different stories about it. This brings another layer to the idea of size. Orion is not just large in space, it is large in time. The version of Orion you see tonight is temporary, a brief arrangement in a long, slow dance of stars that began millions of years ago and will continue long after our species has become a footnote in cosmic history. Now, let your attention drift back to the present, to the simple act of looking up. Even knowing all of this, Orion still feels approachable. He still feels like a companion in the sky, a familiar figure that shows up year after year, season after season. There is comfort in that familiarity, even if the reality behind it is almost too large to fully grasp. And perhaps that is part of the quiet magic of asking how big Orion really is. The answer is not just a number, it is an experience. It is the slow realization that something you can find in a few seconds, with your eyes, contains distances that take light centuries to cross, stars that could swallow planets, and clouds where new suns are quietly being born. Long before telescopes, long before written charts of the heavens, long before anyone thought to measure the distances between stars, people looked up and saw something familiar in the scattered lights of the night sky. They saw a figure standing tall, arms raised, a belt across his waist, and a presence that felt almost intentional. Across continents and centuries, in places that never spoke to one another, this same pattern caught human attention. Tonight, as we let our thoughts drift gently upward again, we are meeting Orion not as a collection of data points or measurements, but as a figure that has walked quietly through human imagination for thousands of years. If you were to step outside on a clear evening and let your eyes adjust to the dark, Orion would likely find you before you find him. In many parts of the world, he rises in the colder months, climbing confidently into the sky as if he knows he belongs there. 3 stars in a neat row draw your gaze almost automatically. That line, simple and steady, becomes an invitation. Follow it, and the rest of the figure begins to assemble itself around your attention. Above the belt, 2 bright points suggest broad shoulders. Below, 2 more hint at feet planted wide apart. One corner glows with a soft reddish tone, another with a crisp blue-white light. Even without knowing their names, you can feel that these stars are not all the same. They each carry a different colour, a different brightness, a different kind of presence. This is often where the human story of Orion begins, with recognition. The moment when random lights stop being random and turn into something meaningful. A hunter, a giant, a hero, a god, a warrior. Depending on where you stand on Earth, Orion takes on a different role, a different personality, a different set of stories. But almost everywhere, he remains a figure of strength, motion, and attention. In ancient Greece, Orion was a great hunter, placed among the stars by the gods. His myths are tangled and dramatic, involving love, betrayal, blindness, and eventual redemption. Some versions say he was killed by a scorpion, which is why the constellation Scorpius rises in the sky as Orion sets, as if the two are forever chasing each other across the heavens. It is a story written not on paper, but in the slow rhythm of the night sky itself. Travel eastward, and Orion becomes something else. In parts of ancient China, the belt stars were seen as part of a larger celestial figure associated with a powerful warrior or ruler. In ancient Egypt, Orion was closely tied to Osiris, the god of the afterlife and rebirth. The rising of Orion in the sky was connected to the flooding of the Nile, an event that brought life and renewal to the land. The stars were not just lights. They were signals, promises, reminders of cycles larger than any single human life. Among the Maori of New Zealand, Orion is known as Tautaru, often associated with the coming of the new year and the changing seasons. In some Native American traditions, the belt stars are seen as hunters or as part of a larger story involving animals and survival. In Japan, Orion is called the Three Stars, simple and direct, a name that reflects how naturally the belt draws the eye. What is striking is not just the variety of these stories, but the consistency of attention. Orion is one of the few patterns in the sky that almost everyone notices, regardless of culture, language, or time period. There is something about the spacing of those stars, the balance of brightness and shape, that feels almost designed to be seen. And yet, behind that familiar figure lies a reality that none of these ancient storytellers could have known. The hunter is not a single being. He is not even a group standing together. He is a chance alignment of stars scattered across a vast region of the galaxy, brought into a single picture only because of where we happen to be standing. Still, the human tendency to connect with the sky is not something to dismiss. It is, in its own way, a kind of early science. By telling stories about the stars, people were paying close attention to their movements, their rising and setting, their seasonal patterns. Orion, in particular, became a marker of time. When Orion appeared in the evening sky, it often signalled changes in weather, in planting seasons, in hunting conditions. The hunter in the sky became a quiet calendar, a way to keep track of the year without written dates or numbered months. His presence meant something practical, not just poetic. If you imagine yourself standing in a field thousands of years ago, with no artificial lights, no screens, no hum of distant cities, the sky would feel much closer. The stars would not be background. They would be part of your world, as present as the ground beneath your feet. Orion rising over the horizon would be an event, something you notice, something you talk about, something you pass down in stories. Now let us gently shift perspective without leaving that sense of human connection behind. Because while Orion has always been a figure in our stories, he is also a collection of very real stars, each one a sun in its own right, burning through its own fuel, living out its own long and complex life. Start again with the belt because it remains the easiest anchor for the eye. The three stars there are known as Al-Nitak, Al-Nilam, and Mintaka. Their names come from Arabic, passed down through centuries of stargazing and navigation. Each one is a massive hot blue star, far larger and more powerful than our sun. They are so bright not because they are close, but because they are truly luminous, pouring out enormous amounts of energy into space. Al-Nilam, the centre star of the belt, is one of the most luminous stars visible to the naked eye. It shines with the power of hundreds of thousands of suns combined, and yet it is so far away that its light still arrives at your eyes as a gentle point in the sky, no brighter than a few other stars nearby. Below the belt hangs what looks like a small, faint smudge. This is the Orion Nebula, though to the unaided eye it might appear as nothing more than a soft blur. Through even a modest telescope it transforms into a glowing cloud of gas and dust, lit from within by newborn stars. This is not a static object. It is a region of active creation, where gravity is slowly pulling material together to form new suns, new planetary systems, and perhaps far in the future, new places where life might one day arise. Above the belt, on one shoulder of the hunter, sits Betelgeuse. Its reddish colour sets it apart immediately. It does not sparkle with the sharp white light of many other stars. Instead, it glows with a deeper, warmer tone, like a distant ember. This colour tells a story about its age and its state. Betelgeuse is a red supergiant, a star nearing the end of its life. It has expanded to an enormous size, and one day, perhaps in the next 100,000 years or so, it will explode as a supernova, briefly shining brighter than entire galaxies. When that happens, the light from that explosion will take centuries to reach Earth, and when it finally does, people living at that time will look up and see a new star in Orion, one that was actually born long before their own ancestors were. On the opposite foot of the hunter is Rigel, a blue supergiant, blazing with intense, high-energy light. Where Betelgeuse is old and swelling, Rigel is young and powerful, burning hot and fast. The two stars mark different stages in the life of massive suns, quietly demonstrating that Orion is not just a picture, but a kind of gallery of stellar evolution. Between these bright anchors are dozens of fainter stars, some visible only under dark skies, others hidden entirely without optical aid. Together they form what astronomers call the Orion OB1 Association, a loose grouping of young, massive stars that likely formed from the same giant cloud of gas millions of years ago. This association stretches across a wide region of space, far beyond the simple outline we draw in the sky. So when you meet Orion in the night sky, you're not just meeting a hunter. You're meeting a star-forming region, a stellar family spread across hundreds of light years, bound not by closeness, but by a shared origin in a long-ago collapse of interstellar clouds. There is something quietly remarkable about that. The figure that once helped people track seasons and tell stories is also a snapshot of a much larger process, one that shapes the structure of our galaxy itself. The Milky Way is filled with regions like this, where stars are born in groups, drift apart over time, and eventually become scattered across the galactic disk. Orion just happens to be one of the closest and most visible of these regions, which is why it stands out so clearly in our sky. Now let your imagination take another step outward. Picture the Earth as a small point, orbiting a modest star on the outskirts of a vast spiral galaxy. From that point, you look toward Orion, toward a region of the galaxy that lies along one of the Milky Way's spiral arms. The light from those stars travels across interstellar space, through thin clouds of gas, past unseen planets and distant suns, until it finally reaches our atmosphere and scatters gently into your eyes. That journey is not direct in the way a thrown stone is direct. It is a long, uninterrupted glide through a medium that is almost, but not quite, empty. Along the way, some of that light is absorbed, some is scattered, and some is reddened by dust. What you see is not exactly what left those stars. It is a version of it, shaped by the space in between. This means that your meeting with Orion is not happening in real time. It is a conversation with the past. You are seeing Betelgeuse as it was hundreds of years ago. You are seeing the Orion Nebula as it was decades ago. You are seeing Rigel as it was nearly a millennium ago. The hunter in the sky is a layered image, built from moments spread across centuries. And yet, it feels immediate. It feels present. That is one of the quiet wonders of stargazing. It connects you to times you cannot reach and places you cannot visit, using nothing more than a line of sight and a bit of patience. There is also something grounding about the way Orion moves through the sky. He rises, he arcs, he sets. Night after night his position shifts slightly, following the slow turning of the Earth. Over the course of a year he disappears into the daytime sky, only to return months later, climbing back into view like a familiar traveller. This rhythm has a way of slipping into human awareness, even if we do not consciously track it. Orion becomes a seasonal companion. His presence marks winter evenings in the north, summer nights in the south. He becomes part of the background of life, a steady figure that outlasts the small changes of daily routines. At the same time, he is not as steady as he seems. The stars are moving. The Earth's axis is slowly wobbling. The galaxy itself is rotating. Over thousands of years, Orion's path across the sky will shift. Over tens of thousands, his shape will change. Over millions, the entire region will be unrecognizable. So when you meet Orion in the night sky, you are meeting a moment. A particular arrangement of stars at a particular time in the long history of the Milky Way. It feels timeless, but it is not. It is a brief chapter in a story that stretches across billions of years. Perhaps that is part of why Orion has held human attention for so long. He stands at the intersection of the familiar and the immense. He is easy to find, easy to recognize, easy to turn into a story. But behind that simplicity lies a depth of space and time that quietly challenges our sense of scale. At first glance, the night sky feels like a flat surface, a kind of dark canvas stretched overhead, with stars pinned into place like glowing beads. When you look at Orion, that impression becomes even stronger. The hunter appears as a tidy arrangement, a clear outline that your eyes can trace without effort. 3 stars in a row for the belt, 2 above, 2 below. A shape that feels almost deliberate, as if someone carefully arranged it for our benefit. But the moment you begin to ask where those stars actually are, not just how they look from here, the sky quietly opens up into something much deeper. Imagine for a moment that you're not standing on Earth. Instead, picture yourself floating in space, far away from our planet, somewhere between the stars. There is no up or down, no horizon, no familiar ground beneath your feet. You turn slowly, and the Milky Way stretches around you in a pale, glowing band. In one direction, you look toward the region where Orion lives. From this new vantage point, the hunter you know begins to fall apart. The belt no longer lines up. The shoulders drift away from the feet. The neat outline dissolves into a scattered collection of lights, each one separated from the others by vast distances. The shape that felt so solid from Earth turns out to be something like a shadow, a projection, a coincidence of perspective. This is the quiet difference between the shape we see and the space we imagine. On Earth, your eyes work a bit like a camera without depth perception for the stars. When you look at a nearby tree, you can tell it is closer than the hill behind it. When you look at a car on the road, you can tell how far away it is by how large it appears and how it moves as you shift your position. But with stars, that natural sense of depth disappears. Everything looks like it lives on the same distant surface, no matter how far apart the objects truly are. So Orion becomes a picture drawn on a flat sky, even though in reality it is a loose, 3-dimensional structure spread across a region of space that would take light centuries to cross. Let us take a gentle walk through that depth, one star at a time, not with numbers alone, but with a sense of spacing, of separation, of how empty and wide the space between these points really is. Start again with the belt, because it is the easiest place to anchor the imagination. From Earth, Alnitak, Alnilam, and Mintaka form a clean, straight line. It feels like they must be close to one another, like beads on the same string. But in reality, they are not lined up side by side in space. They are lined up along your line of sight. Mintaka, one of the belt stars, is actually the closest of the 3, at roughly 200 light-years away. Alnilam, the centre star, sits farther out, around 2,000 light-years from Earth. Alnitak is somewhere in between, at about 1/300 light-years away. That means the belt is not a straight bar in space. It is a long, slanted line, angled away from you, stretching deep into the galaxy. If you could somehow travel from Mintaka to Alnilam, you would not be sliding sideways across a short gap. You would be moving almost 800 light-years deeper into space. That is a journey so long that entire civilizations could rise and fall on Earth, before the light from your departure reached home. Now let your attention drift up to Betelgeuse. From here it looks like a close companion to the Belt, just a short hop away in the sky. But Betelgeuse is much closer to Earth than the Belt stars, sitting at roughly 600 to 700 light-years away. In terms of depth, it is almost halfway between us and Alnilam. So while your eyes connect Betelgeuse and the Belt as part of the same figure, in space they are separated by hundreds of light-years along the line of sight. Rigel, down at the Hunter's Foot, is farther out again, around 860 light-years away. So even within this small outline, you're looking at stars that span a depth of over 1,000 light-years from front to back. This means that when you trace Orion's shape, you're not drawing a flat picture. You're drawing a line that weaves in and out of space, moving closer and farther, back and forth, across an invisible landscape of distance. To make that feel a bit more tangible, try this mental exercise. Imagine a long, dark hallway. At one end near you a small light glows. Farther down the hallway, another light shines. Even farther, near the far wall, a third light flickers. Now stand in just the right spot so that all three lights line up in your view. From where you stand, they look like they are side by side, part of a neat row. But if you were to walk into the hallway, you would discover that they are spread out along its length. This is what the sky is doing, on a scale that makes hallways and buildings and even planets feel like tiny details. Now, step back and look at Orion as a whole, not just the main stars. Surrounding the bright outline is a wider region filled with fainter stars, gas clouds, and dust. Astronomers call this the Orion Molecular Cloud Complex. It is a vast structure, one of the largest nearby star-forming regions in our part of the galaxy. This complex stretches for hundreds of light-years across space. It includes not just the famous Orion Nebula, but a whole family of clouds, dark patches, glowing regions, and stellar groups. Some of these clouds are so dense that they block the light of stars behind them, appearing as inky black shapes against the brighter background of the Milky Way. From Earth, most of this structure is invisible without special instruments. You see only the brightest stars and the faint smudge of the nebula. But in reality, Orion's territory is far larger than the simple figure suggests. The Hunter is just the visible tip of a much broader region of galactic activity. This is where the space we imagine begins to stretch beyond the shape we see. When people talk about constellations, they often imagine them as objects, like a single thing in space. But Orion is more like a window. It is a direction you look, not a place you go. Through that window, you see stars at different distances, clouds at different depths, and light that has travelled for different lengths of time to reach you. The shape you see is an overlay, a human-made connection between points that just happen to line up from our point of view. And yet, that overlay has power. It guides attention. It helps the mind organise the sky. It gives you a way to step into the vastness without feeling completely lost. There is something deeply human about that. Faced with something enormous and complex, we draw a simple shape over it. We give it a name. We tell a story. We make it approachable. Now let us take a moment to imagine what Orion would look like if you could see space the way it really is, in 3 dimensions. Picture each star as a glowing sphere floating in a dark, transparent ocean. There is no background, no flat surface, just points of light at different depths. Some are close enough that their light feels almost immediate. Others are so far away that their glow has been travelling toward you for most of recorded history. Between these stars is not nothing. There is a thin mist of gas, a scattering of dust, the faint presence of magnetic fields and cosmic rays. It is emptier than any vacuum we can create on Earth, but it is not truly empty. Now, in this 3-dimensional space, imagine drawing lines between the stars that make up Orion's outline. Those lines would twist and bend, plunging forward and backward through the star field. They would not form a flat stick figure. They would form a kind of tangled sculpture, one that only looks like a hunter when you view it from one very specific angle. This idea can feel unsettling at first. It challenges the way we naturally think about the sky. but it also adds a new kind of wonder. The night sky is not a ceiling, it is a deep field, a vast volume, a place with thickness and structure. Every time you look up, you're peering into a three-dimensional universe, even if your eyes and brain flatten it into a picture. Now, let us gently shift from the individual stars to the space between them, because that space is part of Orion's size as well. Between Betelgeuse and Rigel, between the belt and the nebula, between every point in the hunter's outline, there are distances so large that our usual sense of travel does not apply. If you could move at the speed of our fastest spacecraft, it would take tens of thousands of years to cross even a small fraction of Orion's region. Light, which seems almost magical in its speed, still needs centuries to make that journey. This means that Orion is not just a large object. It is a large environment. It is a neighbourhood of the galaxy, a place where stars are born, live and die, where clouds collapse and disperse, where gravity slowly shapes the future of entire systems. When you look at Orion, you're not just seeing stars, you're seeing a process. And that process unfolds in a kind of slow motion that is almost impossible to feel. Stars take millions of years to form. They shine for millions or billions of years. They drift apart at speeds that would be imperceptible over a human lifetime. The shape of Orion changes, but it changes on a timescale that makes our own lives feel like brief flashes. This brings us to an interesting contrast. The shape we see feels stable. Orion looks the same year after year. The belt does not wander, the shoulders do not drift. The hunter stands where he always does. But in space, everything is moving. The stars in Orion are orbiting the centre of the Milky Way. They're also moving relative to one another, slowly spreading out as the stellar association they formed in gradually dissolves. Over millions of years, the tight family of young stars will become a loose scattering, and eventually they will blend into the general population of the galaxy. The Orion Nebula itself will not last forever. The intense radiation from its young stars is slowly blowing away the gas and dust that formed them. In a few million years, the nebula will fade, leaving behind a cluster of stars where a glowing cloud once hung. So the space we imagine, when we look at Orion, is not static. It is alive with motion, change, and transformation. Let us take another small step in perspective, one that brings this closer to home. Imagine shrinking the galaxy down to the size of a city. In this model, the Sun might be a house in a quiet neighbourhood. Orion would be a distant district across town, still part of the same city, but far enough away that you do not casually walk there. The stars in Orion would be buildings in that district, some close together, some far apart, with wide streets and open spaces between them. From your house, you can see the lights of that district at night, lined up in a way that forms a familiar skyline. But if you were to travel there, you would discover that the buildings are not arranged in a flat row. They are scattered across blocks and avenues, at different distances from you, forming a three-dimensional cityscape. This is, in a very rough way, what the sky is doing on a cosmic scale. The shape we see is like a skyline. The space we imagine is the city itself. And just like a real city, Orion's region has areas of activity and areas of quiet. The Orion Nebula is like a busy construction zone, full of new stars being built from raw material. Other parts of the region are calmer, filled with older stars that have settled into long, steady lives. Some stars in Orion will live fast and die young, exploding as supernovae and seeding the surrounding space with heavy elements. Others will burn slowly for billions of years, providing stable light to whatever planets might orbit them. All of this is happening within the shape of Orion, even though the shape itself is just a guide for our eyes. Now, let your thoughts drift back to the act of stargazing itself. When you lie back or stand still and look up, you're engaging in a quiet conversation with depth. You're seeing points of light, but your mind is filling in space between them, even if you are not consciously aware of it. That filling in is where imagination lives. You imagine Orion as a figure standing in the sky. You imagine the stars as being part of a single thing. You imagine the space between them as empty, even though it is not truly empty. And in doing so, you create a bridge between your small, grounded experience on Earth and the vast, layered reality of the galaxy. There is no need to let that bridge collapse under the weight of scientific detail. It can hold both. It can hold the simple joy of finding the belt on a cold night, and the deeper understanding that those stars are separated by distances that stretch across centuries of light travel. The shape you see is a kind of invitation, a doorway into a much larger volume of space. The hunter in the sky is not standing on a flat stage. He is suspended in a deep layered environment, one that extends far beyond the lines you draw with your eyes. So the next time you find Orion above you, whether in the real sky or in the quiet space of your thoughts, you might let your gaze linger just a little longer. Let it move past the familiar outline and into the space behind it, into the depth that turns a simple pattern of stars into a wide living region of the galaxy. Instead of beginning with the whole figure this time, let us start with a single point of light, one small anchor in the darkness, and allow the rest of Orion to grow outward from there, just as it often does when you first find him in the sky. Imagine your eyes settling on a faint reddish glow, warmer in tone than most of the stars around it. This is Betelgeuse, the star that marks one of Orion's shoulders, and it often feels like the place where the hunter begins to take shape. Betelgeuse does not sparkle sharply. It glows. There is a softness to its light, a subtle warmth that sets it apart from the colder blue-white stars nearby. Even without knowing anything about astronomy, many people notice this difference. It feels less like a pinprick and more like a distant ember suspended against the black. From here, your gaze naturally wants to move. It drifts downward, guided by the faint sense that there must be more to this point, that it belongs to something larger. And just below Betelgeuse you find yourself arriving at the belt, those three stars that seem almost too perfectly placed to be accidental. Alnitak, Alnilam, Mintaka. Names that sound like echoes from another time, passed down through centuries of stargazers, sailors and storytellers. They form a line that feels steady and reliable, like a ruler laid gently across the sky. From Earth, this line feels horizontal, like a waist or a dividing point between upper and lower halves. But as you trace it, it is worth remembering that this line is not a straight beam in space. It is a visual alignment, a perspective trick that connects stars separated by hundreds of light years into something that looks simple and clean. Still, simplicity has its own quiet beauty. From the belt your eyes often drop just a little farther, and there, hanging like a small pendant, is a faint blur. On a dark night, away from city lights, you can see it without any equipment at all. This is the Orion Nebula, though at this distance it looks more like a soft patch of cloud than anything structured. This little blur sits right in the middle of the hunter's outline, as if someone placed it there on purpose. A gentle reminder that Orion is not just made of stars, but of the space between them as well. Now, let your gaze continue downward, following the imagined line of the hunter's body toward one of his feet. You arrive at Rigel, a star that feels completely different from Betelgeuse. Where Betelgeuse glows red and warm, Rigel shines blue and bright, sharp and clean, like a distant beacon. It is one of the brightest stars in the entire night sky, and it often feels like a kind of exclamation point at the bottom of Orion's form. From shoulder to foot you have just traced a familiar path, one that millions of people have followed with their eyes over thousands of years. It is a simple journey across a small patch of sky, something that takes only a few seconds to complete. But now, let us slow that journey down and stretch it out, not in time, but in space. Because while your eyes move easily from Betelgeuse to Rigel, the distance between those two stars in reality is enormous. Betelgeuse is roughly 600 to 700 light-years away. Rigel sits farther out, around 860 light-years from Earth. That means that when you connect those 2 points in your mind, you are spanning a depth of more than 200 light-years, not just a small sideways step across the sky, and between them, the belt stars sit even farther back, forming a kind of deep background layer behind Betelgeuse and slightly in front of Rigel, so the simple line you draw from shoulder to foot is actually a long winding path through three-dimensional space, one that moves closer to you, then farther away, then a bit closer again. It is like tracing a path through a forest where some trees stand near, some far, and some at a great distance beyond the others, all appearing lined up only because you happen to be standing in just the right spot. Now, let your attention move back up from the belt, not to Betelgeuse this time, but to the other shoulder. There you find Bellatrix, a star that is often overlooked because it does not carry the same fame as Betelgeuse or Rigel. Its name means female warrior in Latin, which feels quietly fitting for a star that holds up one side of the hunter's frame. Bellatrix is hot, blue-white and powerful, though smaller and less luminous than some of Orion's other major stars. It sits at a distance of around 250 light-years, making it one of the closer bright stars in the constellation. That means that, in terms of depth, Bellatrix is much nearer to us than the belt stars or Rigel. So now the top of Orion's shape is not just wide, it is layered. One shoulder sits relatively close in cosmic terms, while the other is hundreds of light-years farther away. And yet, from Earth, they appear side by side, equal partners in the same outline. This is where the pattern we trace becomes something like a gentle illusion, not in a misleading sense, but in a quietly revealing one. It shows us how perspective can turn depth into flatness, how a complex three-dimensional arrangement can be compressed into a simple, two-dimensional picture. Let us continue outward from the shoulders to the arms, because Orion is often drawn as a figure in motion, one arm raised, one lowered, holding a club or a shield depending on the tradition. To one side of Betelgeuse you can find a line of fainter stars that suggest an arm lifting upward. These stars are not as bright or as famous as the main anchors, but they play an important role in giving the hunter his sense of posture. They extend the shape beyond the core, adding width and balance. On the opposite side, near Bellatrix, another line of stars suggests the other arm, reaching outward into the surrounding sky. These stars, too, are spread across different distances, though their individual depths are harder to pin down without detailed measurements. What matters here is not the exact number of light-years, but the feeling of extension. Orion is not just a compact figure. His outline stretches across a wide region of the sky, and behind that outline stretches a wide region of space. If you were to hold your arm out at full length and measure Orion's width from shoulder to shoulder, you would find that he spans about 20 degrees of the sky. That is roughly the width of your open hand against the night. It is a significant patch of darkness, not just a tiny cluster of points. Now imagine that width translated into distance. At the average depth of Orion's stars, that angular width corresponds to a physical span of hundreds of light-years. The hunter's outstretched arms in space would reach across a region large enough to contain countless solar systems, nebulae and star clusters. And yet, the shape still feels compact, manageable, something you can hold in your gaze all at once. This is one of the quiet contradictions of the night sky. The largest structures can feel small, the deepest spaces can feel close. Now let us pause for a moment on the belt again, because it acts like a kind of hinge in Orion's form, a central line from which everything else seems to balance. From the belt, if you follow one direction, you are led to the Orion Nebula. Follow the other, and you are led towards stars that extend into what some traditions imagine as a sword or a scabbard. These stars are fainter, less immediately noticeable, but they add another layer of depth to the pattern. The sword region, which includes the nebula, sits at roughly the same distance as the belt stars, around 1,300 to 2,000 light-years away. This places it deep in the background of the hunter, farther than Betelgeuse and Bellatrix, but not as far as some of the faintest surrounding stars. So in the vertical slice of Orion, you have a kind of cosmic stacking. Closest to you, near the top, is Bellatrix. A bit farther out is Betelgeuse. Farther still are the belt stars and the nebula, And then, down at the foot is Rigel, shining from even deeper space. This layered structure turns the familiar pattern into something like a long slanted bridge across the galaxy, connecting stars that are not neighbours at all, but distant companions brought together by chance alignment. Let us try another way of feeling this distance, one that does not rely on specific numbers. Imagine that each star in Orion is a lighthouse on a vast dark ocean. Some of these lighthouses are closer to you, their beams bright and warm. Others are far out on the horizon, their light faint but steady. From where you stand, all the beams line up into a recognisable pattern, a familiar shoreline. But if you were to sail out into that ocean, you would discover that the lighthouses are scattered across great distances, separated by miles and miles of open water. The shoreline you thought you saw was actually a layered view of many different coasts at once. This is, in a gentle way, what Orion is offering you. A layered view of space, presented as a single figure. Now, let your attention move away from the main stars for a moment, and into the darker spaces between them. These spaces often feel empty, but in Orion they are anything but. The region around Orion is rich with interstellar material. Clouds of hydrogen gas, ribbons of dust, and faint invisible structures stretch between the bright points. Some of these clouds glow faintly when lit by nearby stars. Others absorb light, creating dark patches that stand out against the background of the Milky Way. These clouds are not just scenery, they are the raw material for future stars. The Orion Molecular Cloud Complex is one of the closest and most active star-forming regions to Earth. It is a place where gravity is slowly pulling matter together, building the next generation of suns. So when you trace Orion's pattern, you're not just connecting stars, you're outlining a region of ongoing creation. This adds another layer to the idea of shoulder to foot. It is not just a line across space, it is a path through a dynamic environment, one that has been shaping itself for millions of years and will continue to do so long after this familiar pattern has faded. Now, let us bring this back to the simple, human experience of looking up. There is something deeply satisfying about finding Orion. It is often one of the first constellations people learn, precisely because its shape is so clear. There is a small sense of accomplishment in pointing it out to someone else, in saying, "There it is," and watching their eyes follow your finger across the sky. That moment of recognition is a bridge between the everyday and the cosmic. You're standing on solid ground, breathing familiar air, and at the same time you're engaging with objects that exist hundreds or thousands of light years away. When you trace Orion from shoulder to foot, you're participating in a tradition that stretches back to the earlier sky watchers. You're using your eyes in the same way they did, connecting dots, forming shapes, building meaning from light in the darkness. The difference now is that you can also carry, quietly in the back of your mind, the deeper understanding of what those dots really are. You can know that Betelgeuse is a massive aging star, nearing the end of its life. You can know that the belt stars are young, hot and powerful, born from the same cloud. You can know that the nebula is a nursery, full of stars just beginning their long journeys. And you can know that Rigel, shining so brightly at the hunter's foot, is a giant in its own right, blazing with energy from far deeper in space. All of this knowledge does not have to turn stargazing into a technical exercise. It can simply add texture to the experience, like knowing a little about the history of a place you love to visit. Now, let us take one more step outward, one that connects Orion's pattern to the larger structure of the sky. The belt stars in particular act as a kind of pointer. If you follow their line in one direction, it leads you to Sirius, the brightest star in the night sky. Follow it the other way, and it leads you toward the red star Aldebaran and the Pleiades cluster. This means that Orion is not an isolated figure. It is part of a network of visual pathways that connect different regions of the sky. The hunter's shape becomes a kind of guide, helping you navigate a much larger celestial landscape. This too adds to the sense of size. Orion is not just big in itself, it is big in context. It sits at the centre of a web of relationships between stars and constellations, a hub in the map of the night. Rather than beginning with a number or a measurement this time, let us begin with a feeling. Imagine standing outside on a cold, clear night, your breath faintly visible in the air, your eyes slowly adjusting to the darkness. You find Orion again, as you have before, and your gaze drifts naturally to that soft, reddish point near the top of the figure. It does not shout for attention the way some bright stars do. It simply glows, steady and warm, like a distant coal in a very large, very quiet fire. That is Betelgeuse, and even before you know anything about its size or its nature, it already feels different. There is something about colour in the night sky that draws the eye. Most stars appear white or pale blue, sharp and clean against the black. Betelgeuse stands apart. Its light carries a subtle orange-red tint, gentle but noticeable, as if it belongs to another category of object entirely. This difference is not just a trick of the atmosphere or your eyes. It is a clue, a quiet hint about what is happening deep inside that star, far beyond the reach of any telescope. Betelgeuse is a red supergiant, which is a term that sounds dramatic because it is describing something truly dramatic. This is not a star like our Sun, modest in size and steady in its middle age. This is a star that has grown enormous, swollen to hundreds of times the diameter of the Sun, a star that has reached a late stage in its life and is now living on borrowed time, at least by stellar standards. To begin understanding how big Betelgeuse really is, it helps to think about what a star is doing over the course of its life. When a star is born, it forms from a collapsing cloud of gas and dust. Gravity pulls material inward, the core heats up, and eventually nuclear fusion ignites. Hydrogen atoms begin to fuse into helium, releasing energy that pushes outward, balancing the inward pull of gravity. For most of a star's life, this balance holds. The star shines steadily, neither collapsing nor exploding, simply existing in a long, stable phase that can last billions of years. Our Sun is in this stage right now. It has been for about 4.6 billion years, and it will remain there for several billion more. It is a quiet, reliable star, well behaved on the cosmic scale. Betelgeuse, however, was never destined for such a long, calm life. From the moment it formed, it was massive. Stars that begin their lives with a great deal of mass burn through their fuel much more quickly. They live fast, bright and hot, and they do not stay in their stable phase for very long. After Betelgeuse exhausted the hydrogen in its core, the balance that held it steady began to shift. The core contracted and heated up, and new layers of fusion ignited around it. As this happened, the outer layers of the star expanded outward, far into space. The surface cooled as it spread out, changing the star's colour from blue-white to red-orange. This is how a red supergiant is born, not as a separate kind of star, but as a phase in the life of a very massive one. So when you look at Betelgeuse, you're not just seeing a star that is big. You're seeing a star that is in the later chapters of its story, a star that has changed shape and character as it has burned through its internal fuel. Now let us talk about size, but in a way that stays connected to something familiar. Imagine placing Betelgeuse where our Sun is, right at the centre of our solar system. The Sun's surface extends a little less than 1 million kilometres in radius. Betelgeuse's surface, by contrast, would extend outward so far that it would swallow the orbits of the inner planets without much effort. Mercury would disappear first, then Venus, then Earth, then Mars. Depending on exactly how large Betelgeuse is at a given moment, even Jupiter's orbit might be brushed by the star's outer layers. The region where our solar system currently holds rocky worlds, gas giants, and icy moons would instead be filled with the thin glowing atmosphere of a single enormous star. That is not just big. That is a scale that turns our usual sense of planetary space into something very small, and yet Even this comparison does not fully capture what makes Betelgeuse remarkable, because its size is not fixed. It changes. Betelgeuse is what astronomers call a variable star. Its brightness and its radius fluctuate over time. The star expands and contracts in slow, rhythmic pulses like a deep cosmic breath. These changes happen over periods of months to years, and they can be detected even from Earth as subtle shifts in how bright the star appears in the sky. So when we say Betelgeuse is enormous, we're not talking about a static object. We're talking about something that swells and shrinks, that refuses to hold a single tidy measurement. This makes Betelgeuse feel almost alive in a way that is easy to connect with. It is not a rigid, unchanging point of light. It is dynamic, active, and restless. Now let us step back for a moment and think about where Betelgeuse sits in space, because its size becomes even more striking when you place it in its broader context. Betelgeuse is part of the Orion region, but it is closer to Earth than many of the other major stars in the figure. At roughly 600 to 700 light-years away, it is still incredibly distant by human standards, but it is practically a neighbour compared to the belt stars, which lie much farther out. This means that Betelgeuse's apparent size in the sky is not just a result of its true size, but also of its relative closeness. Even so, its surface is so large that astronomers have been able to resolve it as a disk, not just a point, using advanced telescopes and techniques. This is a rare achievement. Most stars, even large ones, appear as tiny dots, no matter how powerful the telescope. But Betelgeuse's bloated, extended atmosphere spreads its light over a wide enough area that it can be imaged as something with shape and structure. Astronomers have seen bright patches, dark regions, and huge plumes of gas rising from its surface, like vast, slow-moving storms. These plumes are not small. They are so large that each one could stretch across the entire orbit of Earth and still have room to spare. This gives Betelgeuse another layer of scale. It is not just a big ball of gas, it is a complex, active environment, with motion and structure on a scale that makes even planetary systems look compact. And then there is the matter of mass. While Betelgeuse's outer layers are spread thin across an enormous volume, the star itself is not especially dense. In fact, if you could somehow place Betelgeuse in a giant imaginary bathtub, it might float. Its average density is lower than the density of air at Earth's surface. This is not because it is light in mass. Betelgeuse contains many times the mass of our Sun. It is because that mass is distributed across such a vast space that the star becomes, in a sense, very fluffy. So here we have a star that is massive, enormous in size, and yet, in terms of density, surprisingly delicate. Now let us bring time back into the picture, because Betelgeuse's refusal to stay small is not just about its current state, it is also about where it is headed. Red supergiants like Betelgeuse are not stable in the long term. The processes happening in their cores are leading them toward a dramatic end. As Betelgeuse continues to burn through heavier and heavier elements, its internal structure becomes more layered and more unstable. Eventually it will reach a point where it can no longer generate enough energy to support itself against gravity. When that happens, the core will collapse in a fraction of a second, and the outer layers will be blasted into space in a supernova explosion. When Betelgeuse goes supernova, it will become one of the brightest objects in the sky, possibly visible even during the day. For weeks or months it will outshine entire galaxies. The light from that explosion will travel outward in all directions, carrying with it the heavy elements forged in the star's core. Those elements, things like carbon, oxygen, and iron, will eventually become part of new stars, new planets, and perhaps new forms of life. So Betelgeuse's size is not just a feature of its present. It is part of a long process of creation and transformation that stretches far into the future. Now let us return, gently, to the experience of looking at it from Earth. When you see Betelgeuse in Orion's shoulder, you're seeing light that left the star hundreds of years ago. That means the Betelgeuse you see tonight is not exactly the Betelgeuse that exists right now. It may be slightly larger, it may be slightly smaller, it may be in a different phase of its slow pulsation. It could even, in theory, have already gone supernova, its explosion still travelling toward us across the vast distance of space. This is not something to worry about. The odds are that Betelgeuse is still there, still glowing, still breathing in its slow, stellar way. But the possibility itself adds another layer to the sense of scale. You're not just seeing something far away, you are seeing something in the past. This turns Betelgeuse into a kind of time marker, a glowing reminder that the universe operates on timescales that stretch far beyond our own. Now, let us connect Betelgeuse back to the larger question of Orion's size, because this star does not exist in isolation. Betelgeuse is part of a loose association of stars that formed from the same general region of space. It shares a kind of family history with some of the other stars in Orion, even though they are now spread across hundreds of light years. This means that when you look at Betelgeuse, you are looking at one member of a much larger stellar community, a community that spans a wide region of the galaxy. And Betelgeuse, in all its enormity, is just one point in that region. This is where the idea of size becomes layered again. Betelgeuse is huge compared to our Sun. The Orion region is huge compared to Betelgeuse. The Milky Way is huge compared to Orion. And the universe is huge compared to the Milky Way. Each step outward makes the previous one feel smaller, not because it is small, but because the scale keeps expanding. Now, let us take a moment to imagine what it would be like to approach Betelgeuse, not physically but visually. Picture yourself in a spacecraft drifting slowly through space, leaving the familiar outline of Orion behind. The stars around you grow brighter and more distinct. Betelgeuse looms ahead, no longer a point, but a vast glowing sphere filling more and more of your view. As you get closer, the star's surface resolves into something like a churning sea of light and gas. Huge convective cells rise and fall, each one larger than the distance from the Earth to the Sun. Darker regions and brighter regions shift and change over time, driven by the flow of energy from deep within the star. There is no solid surface to land on, no firm boundary where the star ends and space begins. The atmosphere of Betelgeuse fades gradually into the surrounding space, a thin veil of gas extending far beyond what you would normally think of as the star's edge. This makes Betelgeuse feel less like an object and more like an environment, a place rather than a thing. Now bring that imagined closeness back to the reality of where you are, sitting or lying comfortably, listening, perhaps with your eyes closed. That vast, dynamic, restless star is hanging in the sky above you, reduced to a small, warm point of light by distance alone. This contrast is one of the quiet joys of thinking about stars. It lets you hold two very different experiences at once. The simple, gentle beauty of a glowing dot in the sky, and the overwhelming scale of what that dot truly represents. Betelgeuse, in a way, embodies the entire theme of Orion's size. It looks approachable, even friendly, a soft light in a familiar shape. But it is anything but small. It is a giant, nearing a spectacular end, part of a vast region of space filled with creation and change. So let Betelgeuse linger in your mind for a moment longer, glowing steadily at the hunter's shoulder, a reminder that even a single point of light in the sky can contain a volume of space large enough to swallow entire worlds. Rather than beginning with warmth and swelling like we did with Betelgeuse, let us begin this time with sharpness. Picture your eyes adjusting to the dark again, the sky settling into that familiar deep tone where stars begin to separate themselves from the background. You find Orion's belt as usual, and then let your gaze slide downward along the imagined line of the hunter's form. At the far end of that path, one star stands out with a kind of crisp confidence. It does not glow softly. It shines, clean, blue-white, and unmistakably bright. This is Rigel, the star that marks the hunter's foot, and in many ways it feels like the edge of Orion's territory. Rigel's light has a different quality from Betelgeuse's. Where Betelgeuse feels like an ember, Rigel feels like a blade of ice catching the light. Its colour is not warm. It is cool, almost electric. This difference is not subtle. Even people who have never learned the names of stars often notice that Orion seems to have one star that looks red and another that looks blue. Those 2 points act like bookends for the entire figure, showing you without words that stars can live very different kinds of lives. Rigel is a blue supergiant, a type of star that sits near the opposite end of the stellar life cycle from Betelgeuse, even though both are massive and luminous. Blue supergiants are hot, young, and incredibly powerful. They burn their fuel at a fierce pace, pouring out enormous amounts of energy into space. If Betelgeuse feels like a star that has expanded and softened with age, Rigel feels like a star that is still tightly focused, still blazing with youthful intensity. Now, let us talk about what bright really means in this context, because Rigel's brightness in the sky can be misleading in an interesting way. When you look at Rigel from Earth, it appears as one of the brightest stars in the entire night sky. It is usually ranked among the top 10, often competing with stars that are much closer to us. But Rigel is not close. It sits around 860 light-years away. That means the light you see tonight left Rigel sometime in the Middle Ages, long before modern science, long before telescopes, long before most of the world's current cities existed. For a star that far away to appear that bright, it has to be truly luminous. Rigel shines with the power of tens of thousands of suns. Some estimates put its luminosity at around 40,000 to 120,000 times that of our Sun, depending on how it is measured and which part of its spectrum you focus on. That is not a gentle glow. That is an enormous outpouring of energy, flooding the surrounding space with light and radiation. To get a sense of what that means, imagine replacing our Sun with Rigel. The Earth would not just warm up, it would be instantly sterilized. The oceans would boil away, the atmosphere would be stripped. The region where our solar system now hosts quiet orbits and stable climates would become an intense, hostile environment dominated by overwhelming radiation. So while Rigel looks like a simple point of light, it is, in reality, a kind of cosmic furnace, blazing away in the depths of space. Now let us shift from brightness to size, because Rigel is not just powerful, it is also enormous. Rigel's radius is roughly 70 to 80 times that of the Sun. If you were to place Rigel at the centre of our solar system, its surface would extend well past the orbit of Mercury and possibly reach toward Venus. It would not swallow the entire inner solar system the way Betelgeuse might, but it would still dominate the space in a way that makes planets feel like small details around a vast glowing sphere. This gives Rigel an interesting contrast with Betelgeuse. Betelgeuse is larger in physical size, but Rigel is hotter and often more luminous. One is a swollen aging giant. The other is a compact blazing powerhouse. Together they frame Orion as a place where very different kinds of massive stars coexist, each one telling a different story about what it means to be big in the universe. Now, let us place Rigel back into the three-dimensional space of Orion, because its position adds another layer to the sense of scale. Rigel sits farther away from Earth than Betelgeuse, but closer than some of the belt stars. This places it in a kind of middle layer of Orion's depth. When you draw a line in your mind from Betelgeuse, past the belt, down to Rigel, you're not moving in a flat plane. You're moving forward and backward through space. Rigel is not directly below the belt in the way the drawing suggests. It is offset in depth, sitting hundreds of light-years behind some stars and hundreds of light-years in front of others. This means that the edge of the hunter, as marked by Rigel, is not an edge in the physical sense. It is an edge only in the picture we see from Earth. In reality, the Orion region extends beyond Rigel, both closer to us and farther away. There are stars and clouds behind it, around it, and in front of it, even if they do not stand out in the familiar pattern. So Rigel becomes less like a boundary and more like a signpost, a bright marker that draws your eye to one end of a much larger invisible structure. Now let us take a moment to think about Rigel as a system, rather than a single star, because like many massive stars, Rigel does not live alone. Rigel is part of a multiple star system. The main blue supergiant you see is accompanied by smaller, fainter companion stars that orbit around it. These companions are much less luminous, and often lost in the glare of the primary star when viewed from Earth. This means that when you look at Rigel, you're not just seeing one star. You're seeing the dominant member of a small stellar family, a group of suns bound together by gravity, moving through space as a unit. This adds another layer of scale. The Hunter's Foot is not a single point. It is a small system, a cluster of stars travelling together across the galaxy. Now, let us connect Rigel back to the broader environment of Orion, because this star is not just a bright object in isolation. It plays a role in shaping the space around it. Massive hot stars like Rigel emit intense ultraviolet radiation. This radiation interacts with the surrounding gas and dust, heating it, ionizing it, and in some cases pushing it away. Over time, this can carve out cavities in nearby clouds, creating bubbles of hot, thin gas surrounded by denser material. So in the wider Orion region, stars like Rigel are not just passive residents, they are active sculptors. They help shape the structure of the star-forming clouds, influencing where new stars can and cannot form. In this way, Rigel's size is not just a matter of how big it is physically, it is also about how far its influence reaches. The light and radiation from Rigel travel outward for hundreds of light years, interacting with the environment of Orion long after the star itself has moved on, or changed. Its presence leaves a kind of energetic footprint in the surrounding space. Now, let us return to the simple, human experience of finding Rigel in the sky, because all of this cosmic influence is hidden behind a very small visual moment. From Earth, Rigel is just a bright dot near the bottom of Orion's figure. You might point to it and say, that's his foot, and move on. But that small dot represents a star so luminous that it outshines tens of thousands of suns, a system of multiple stars bound together, and a source of radiation that shapes the surrounding region of the galaxy. This contrast between appearance and reality is one of the recurring themes when you explore Orion's size. Things that look small are often vast. Things that look simple are often layered and complex. Now, let us bring time back into the picture again, because like Betelgeuse, Rigel is not frozen in a single moment of its life. Rigel is still in a relatively early stage of its evolution, at least compared to Betelgeuse. It is burning hydrogen in its core or in surrounding layers, maintaining a strong balance between gravity and outward pressure, but it will not stay this way forever. As a massive star, Rigel is destined for a dramatic future. Over millions of years it will exhaust its fuel, change its internal structure, and eventually, like Betelgeuse, it will reach a point where it can no longer support itself. When that happens, it too will likely explode as a supernova. This means that both ends of Orion's familiar figure are marked by stars that will one day die in spectacular fashion, scattering heavy elements into space and contributing to the next generation of stars and planets. So the Hunter's form is not just a static picture, it is a snapshot of a region where creation and destruction are both quietly at work. Now, let us imagine, just for a moment, what it would be like to approach Rigel in the same way we imagined approaching Betelgeuse. Picture your spacecraft drifting through the Orion region, passing between stars and faint clouds of gas. Rigel grows larger in your view, its blue-white light becoming more intense, more blinding. As you draw closer, the star's surface resolves into a brilliant, glowing expanse, far hotter and more energetic than Betelgeuse's. The star's radiation bathes everything around it in a harsh, luminous glow. There is no gentle warmth here. This is a place of intense energy, where the environment is shaped by light itself. And yet, like Betelgeuse, Rigel does not have a solid surface. Its atmosphere, too, fades gradually into space, a glowing envelope of gas extending far beyond what you might expect from a simple sphere. This makes Rigel, once again, feel less like an object and more like a region, a zone of influence rather than a defined solid body. Now let us bring that imagined closeness back to the reality of your current position. You are here on Earth, looking at a star that exists hundreds of light years away. The light you see is ancient by human standards. The star itself may have changed in small ways since that light began its journey. And yet, in your sky, it appears steady, reliable, a constant marker in Orion's shape. This tension between change and stability is another quiet layer of scale. The universe is always in motion, always evolving, but from our short-lived perspective, it often feels still. Rigel stands as a reminder that even the brightest, most powerful stars are part of a long, slow process of transformation. Now, let us connect Rigel back to the larger question of Orion's size in a more direct way. If you were to map out the positions of Orion's major stars in 3 dimensions, you would find that Rigel sits near one edge of the region, but not at a true boundary. The Orion OB1 association, the loose group of young, massive stars that includes many of Orion's brightest points, stretches beyond Rigel in some directions and in front of it in others. This means that the edge of the hunter is not a physical edge. It is a visual one. The real region of Orion is more like a wide, irregular cloud of stars and gas, with no clear borders, fading gradually into the surrounding parts of the Milky Way. Rigel just happens to be one of the brightest beacons on that cloud, making it feel like a natural endpoint for the shape we draw. So when you trace Orion from shoulder to foot and stop at Rigel, you're not reaching the end of something in space. You're reaching the end of a line in your mind. Beyond that line, the galaxy continues, filled with more stars, more clouds, more regions just as vast and complex as Orion itself. This brings us back gently to the experience of scale. Orion, as a shape, fits between your outstretched hands. Orion, as a region of space, spans hundreds of light years, and Rigel, as a single point at the edge of that shape, is a star so powerful and luminous that it could dominate an entire solar system if it were placed at its centre. Each level of viewing adds another layer to the sense of size. So let Rigel linger in your thoughts for a moment, shining sharply at the hunter's foot, a blue beacon marking one corner of a vast, layered region of the galaxy. Somewhere between the sharp blue light of Rigel and the warm glow of Betelgeuse, your eyes almost always pause on a simple, steady line of 3 stars. It does not demand attention the way the brightest points do. It does not shimmer with colour or intensity. Instead, it waits, calm and balanced, as if it were placed there to hold the entire figure together. This is Orion's belt, and in many ways it feels like the quiet centre of the hunter, the part of the sky that everything else seems to revolve around. When people learn to find Orion for the first time, the belt is usually the starting point. 3 stars in a row, evenly spaced, easy to spot even under less than perfect skies. If you can find those 3, you can build the rest of the constellation around them. They act like a foundation, a reference line, a kind of celestial ruler laid gently across the darkness. Yet, as with so much in the night sky, what looks simple and compact turns out to be wide, layered, and deeply connected to the space around it. The 3 stars that form the belt have names that carry the sound of distant languages and long traditions: Alnitak, Alnilam, and Mintaka. These names come from Arabic, passed down through medieval star charts and navigational guides, echoes of a time when the sky was one of the most important maps a person could have. From Earth, these 3 stars appear almost perfectly aligned. The spacing between them feels intentional, as if they were set out in a careful pattern. But this alignment is another gift of perspective. In space, they are not standing side by side like fence posts. They are staggered in depth, each one at a different distance from us, connected into a line only by our point of view. Mintaka, one end of the belt, is the closest of the 3. Alnitak sits a little farther away. Alnilam, the middle star, is the most distant. lying far deeper into the Orion region. When you draw a straight line across the sky connecting them, you're actually tracing a path that slopes away from you, stretching hundreds of light years into the galaxy. This alone begins to change the sense of what the belt really is. It is not a short bar across the hunter's waist. It is a long, angled line of stars reaching deep into space, a bridge between nearer and farther parts of Orion's region. Now, let us slow down and meet these three stars not just as points in a pattern, but as individual suns, each one with its own story, its own scale, and its own influence on the space around it. Alnitak, the easternmost star of the belt, is a massive, hot, blue star, far larger and more luminous than our Sun. It is actually a multiple star system, with at least 3 stars bound together by gravity. The main star dominates the system, pouring out intense ultraviolet radiation into the surrounding space. This radiation does not simply travel outward and vanish. It interacts with nearby clouds of gas and dust, lighting them up, shaping them, and sometimes pushing them aside. Near Alnitak there are glowing regions of nebulae, clouds that shine because they are being energized by the star's light. In this way, Alnitak is not just a star in the belt. It is an active participant in the environment of Orion, a source of energy that helps define the appearance of the region itself. Move your attention to the center star, Alnilam. This is one of the most luminous stars visible to the naked eye, even though it is also one of the most distant among Orion's bright points. Alnilam shines with the power of hundreds of thousands of suns combined. It is so bright that even from nearly 2,000 light-years away, it stands out clearly in our sky. Alnilam is a blue supergiant, hot and enormous, radiating energy at a tremendous rate. Its surface temperature is many times hotter than the Sun's, giving it that clean white-blue light that feels almost sharp against the darkness. Then there is Mintaka, the westernmost star of the belt. Like Alnitak, Mintaka is also a multiple star system. Its main star is another hot, massive blue giant shining with intense light. Mintaka is notable for something else as well. It lies very close to the celestial equator, the imaginary line in the sky that divides the northern and southern hemispheres. This means that, depending on where you stand on Earth, Mintaka can appear just above or just below the horizon, a small detail that quietly connects the belt to the way our planet is tilted and oriented in space. So even within this simple line of 3 stars there is complexity, multiple star systems, enormous luminosities, connections to the surrounding nebulae, and a range of distances that turn a flat line into a slanted 3-dimensional structure. Now, let us step back from the stars themselves and look at what the belt does in the larger picture of the sky. The belt is not just a feature of Orion, it is also a guide. If you follow the line of the belt in one direction, it leads you to Sirius, the brightest star in the entire night sky, part of the constellation Canis Major. Follow it the other way, and it leads you toward Aldebaran, the red eye of Taurus, and beyond that to the Pleiades, a small cluster of stars that has captured human attention for as long as Orion has. This makes the belt something like a pointer, a quiet arrow laid across the sky, connecting different regions of the Milky Way into a single visual pathway. In this sense, it does not just bind the hunter together, it binds the sky itself, linking constellations into a broader navigable map. For ancient travellers and navigators, this kind of connection was more than a curiosity. It was practical. The belt could help you find directions, estimate time, and orient yourself under the open sky. Even now, in a world filled with screens and satellites, there is something grounding about using a line of stars to find your way. But let us return to the idea of size, because the belt's role as a binding feature becomes even more interesting when you consider how much space it actually spans. From one end of the belt to the other, you're looking across a region that covers hundreds of light years in depth, and behind the belt, hanging like a soft shadow, is the Orion Nebula, one of the most famous star-forming regions in the sky. This nebula is not a small cloud. It is a vast structure, about 24 light-years across, filled with gas and dust that is actively collapsing to form new stars. Inside it, there are clusters of young stars, some only a few million years old, surrounded by swirling disks of material that may one day become planets. The belt stars sit in front of this nebula from our point of view, like a set of bright markers against a deeper glowing background. But in space, they are part of the same general region, a loose family of stars and clouds that formed from a giant molecular cloud millions of years ago. This means that the belt is not just a line drawn across empty space. It is a line drawn across a living environment, a place where stars are being born, where light and gravity are shaping the future of the region. Now, let us take another step outward and imagine what this looks like from a perspective far beyond Earth. Picture yourself floating hundreds of light years away, somewhere off to the side of the Orion region. From there, you turn and look back. The neat line of the belt is gone. The three stars no longer line up. They form a scattered triangle or an uneven grouping, each one clearly separated from the others by wide gaps. The Orion Nebula, which from Earth appears as a small blur beneath the belt, now spreads out into a wide, complex cloud filled with structure and depth. The entire region looks less like a stick figure and more like a loose cluster of activity, a patch of the galaxy where something is happening. This shift in perspective highlights a quiet truth. The belt binds the sky together for us, but only because of where we stand. It is a product of viewpoint, not a physical connection, and yet that does not make it less meaningful. It simply makes it more human. Now, let us return to the experience of looking up from Earth, because this is where the belt truly comes into its own. On a clear night, away from bright city lights, the belt seems to hover in the sky, perfectly balanced. It is often one of the first things you notice, even before you consciously recognize Orion. There is a sense of symmetry to it, a kind of visual calm. That calm is part of why the belt has played such a central role in so many cultural stories and interpretations. In ancient Egypt, the belt was sometimes associated with the soul's journey after death. In some traditions, the three stars were seen as three kings, three sisters, or three hunters. The number itself seems to invite meaning, a trio standing together in the vastness of the night. But behind these stories is the physical reality of three massive stars, each one burning through its fuel at a tremendous rate, each one destined for a relatively short and dramatic life. Massive stars like those in Orion's belt do not last billions of years the way smaller stars do. They live for only a few million years before they change and eventually die, often in supernova explosions that scatter heavy elements into space. This means that the belt, as we see it now, is a temporary arrangement, not just in terms of shape, but in terms of the stars themselves. These three bright points will not always be there. In a few million years, some or all of them will have ended their lives, leaving behind remnants like neutron stars or black holes, surrounded by expanding shells of glowing gas. So the belt binds the sky together for us now, in this moment of cosmic time, but it is not a permanent fixture in the long story of the galaxy. Now let us consider how the belt fits into the larger structure of the Milky Way, because this adds another layer to the idea of scale. The Orion region lies within one of the Milky Way's spiral arms, often called the Orion Arm or the Local Arm. This is a region filled with star-forming clouds, young stars and stellar associations. It is a place of activity, a kind of galactic neighbourhood where new suns are regularly being born. The belt stars are part of this larger structure. They are not isolated objects floating in empty space. They are members of a vast dynamic system that stretches across tens of thousands of light years, wrapping around the galaxy's centre in a graceful spiral. So when you look at the belt, you're not just seeing three stars, you're seeing 3 points in a much larger pattern, one that extends far beyond the boundaries of Orion itself. This brings us back to the idea of binding, but on a different scale. The belt binds Orion's shape together in the sky. The Orion region binds a group of stars and clouds together in space. The spiral arm binds many such regions together into a structure that defines part of the Milky Way. And beyond that, the galaxy itself is part of a group of galaxies, bound together by gravity in a vast cosmic web. Each level of structure is connected to the next, like a series of nested patterns, each one larger than the last. Now, let us return, gently, to the simple act of finding the belt again. Perhaps you're imagining it now, 3 steady points of light in a dark field. There is a kind of quiet satisfaction in that image, a sense of balance and order. That sense does not have to disappear when you think about the immense scale behind it. In fact, it can deepen it. You can hold both ideas at once. The belt is a simple, familiar guide in the sky, and the belt is a line of massive stars, part of a vast 3-dimensional region of the galaxy, burning brightly in a relatively brief moment of cosmic history. Now, let us take a moment to think about motion, because even though the belt looks still, it is not. The stars in the belt are moving through space, orbiting the centre of the Milky Way along with everything else in our galaxy. They are also moving relative to one another, slowly drifting apart as the loose stellar association they belong to spreads out over time. This motion is incredibly slow from our perspective. Over a human lifetime you would not notice any change in the belt's shape. But over tens of thousands of years the alignment will shift. Over millions of years the familiar line will break apart. This means that the belt, like the rest of Orion, is a temporary pattern, a momentary alignment in a long, slow dance of stars. Now, let us imagine, just for a moment, what it would be like to travel along the belt, not physically, but conceptually. Picture yourself starting near Mintaka, drifting through the space around that star. The region is bathed in intense light, the surrounding gas glowing faintly where it is energized by radiation. You move deeper into the Orion region, toward Alnilam, crossing hundreds of light years of thin, dark space, passing by faint stars and invisible clouds. Then you continue on toward Alnitak, entering another zone of glowing nebulae and active star formation, where the light from massive stars shapes the surrounding environment. This journey, in reality, would take hundreds of years even at the speed of light. But in the mind, it happens in moments, a gentle drift through an imagined space. This contrast between mental travel and physical distance is another way the belt binds the sky together. It lets you move in thought across vast regions of space with nothing more than a shift of attention. Now, let us connect this back to the larger theme of Orion's size. The belt is often the part of Orion that feels most approachable, most manageable. 3 stars in a row, easy to find, easy to remember. But behind that simplicity is a depth of space that stretches across centuries of light travel, a complexity of stellar systems, and a connection to one of the most active star-forming regions in our part of the galaxy. So when you look at the belt, you are looking at something that is both small and vast at the same time. It is small enough to fit neatly in your field of view. It is vast enough to contain worlds, nebulae, and stars that will outlast entire civilizations. If you were to step outside right now and tilt your head back, the word up would probably feel simple. It would feel like a direction, a way to point your eyes away from the ground and toward the open sky. You might see stars, maybe clouds, maybe the faint glow of the moon or the soft haze of distant city lights. All of it would seem comfortably placed on a kind of invisible dome above you, close enough to feel present, far enough to feel unreachable, somewhere in between, quietly labelled as up there. But the moment you begin to ask how far up there actually is, that comfortable idea starts to stretch. Because up is not a single place. It is not even a layer. It is a deep, layered volume of space that extends outward in stages, each one far beyond the last, each one making the previous feel almost close by comparison. Let us begin, gently, from where you are. Right now, you're sitting or lying on the surface of a planet with a thin shell of air wrapped around it. This atmosphere extends upward for about 100 kilometers before it fades into what we usually call space. That distance, by everyday standards, is already large. You could not drive it in an afternoon. You could not walk it in a day. And yet, in cosmic terms, it is almost nothing. At about 400 kilometers above your head, the International Space Station circles the Earth. It takes astronauts about 8 minutes to get there in a rocket. That feels impressive. That feels far. But it is still hugging the planet, skimming just above the edge of the atmosphere like a stone skipping across water. Beyond that, at around 384,000 kilometers, sits the Moon. Light takes about 1¼ seconds to travel that distance. If you were to send a message to someone standing on the Moon using a beam of light, you would see it arrive almost instantly. On the scale of the universe, that is practically right next door. Now, move a little farther out. At about 150 million kilometers from Earth is the Sun. Light takes around 8 minutes to cross that gap. If the Sun were to suddenly go dark, you would continue to feel its warmth and see its light. For those 8 minutes before anything changed, that distance begins to feel less like a step and more like a true stretch of space. Beyond the Sun's immediate neighbourhood, the planets spread out: Jupiter, Saturn, Uranus, Neptune. Each one marks another layer of up there, another ring of space around our star. Far beyond the outer planets lies the Kuiper Belt, a region filled with icy objects and remnants from the formation of the solar system. Beyond that, even farther, is the Oort cloud, a vast, spherical halo of debris that may extend halfway to the nearest star. At this point you have travelled, in your imagination, a distance of about 1 to 2 light years from Earth. Light, which felt so fast when crossing the gap to the Moon, now needs an entire year or more to make the journey, and still you have not left our Sun's sphere of influence. Now let us take the next step outward, because this is where up there begins to feel truly distant. The nearest star to our Sun, Proxima Centauri, is about 4.124 light-years away. That means the light you see from it tonight began its journey more than 4 years ago. If you could travel at the speed of our fastest spacecraft, it would take tens of thousands of years to reach it. And yet, in the grand structure of the Milky Way, Proxima Centauri is practically a neighbour across the street. Our galaxy is about 100,000 light-years across. It contains hundreds of billions of stars. The region around our Sun is just one small patch in a vast rotating disk of gas, dust and light. Now, with that scale in mind, let us bring Orion back into the picture. When you look at Orion, you're not looking at something just beyond the Moon, or just beyond the Sun, or even just beyond the nearest stars. You're looking deep into the galaxy, toward a region hundreds and sometimes thousands of light-years away. So when you ask how far up there is in the direction of Orion, the answer is not a single number. It is a range. Betelgeuse, the warm shoulder of the Hunter, sits roughly 600 to 700 light-years away. Rigel, the sharp blue foot, is around 860 light-years distant. The belt stars reach even farther, with Alnilam lying close to 2,000 light-years from Earth. The Orion Nebula, glowing faintly beneath the belt, sits at about 300 light-years away. This means that when you look at Orion, you're not looking at a single distance. You're looking across a layered field of space, a kind of cosmic depth map, where different parts of the figure exist at very different up-theres. To make that feel a bit more grounded, imagine standing on a long straight road at night. Close to you there are streetlights. Farther down, there are house lights. Farther still, there are the faint lights of a distant town. From where you stand, all of those lights appear on the same line, part of the same view, but in reality, they are spread out over miles and miles of distance. Orion is like that, but instead of miles, the distances are measured in hundreds and thousands of light-years. Now, let us take a moment to think about what a light-year really means, because the term itself can sometimes hide as much as it reveals. A light year is not a unit of time, it is a unit of distance. It is the distance light travels in 1 year. That distance is about 9.46 trillion kilometres, or roughly 6 trillion miles. Those numbers are so large that they can feel abstract, like they belong to a different kind of thinking altogether. So let us try a different approach. Imagine you could drive a car that never needed to stop, never ran out of fuel, and could travel at a constant speed of 100 kilometers per hour. At that speed, to travel 1 light year, it would take you more than 10 million years. So when you hear that Betelgeuse is 600 light years away, you're talking about a journey that would take, at that speed, 6 billion years. And when you hear that Alnilam is nearly 2,000 light years away, you are talking about a journey that would take tens of billions of years, longer than the current age of the universe. This is not to suggest that such a journey is something we should imagine actually taking. It is simply a way to let the scale sink in, gently and slowly. Now, let us return to the experience of looking up, because this is where the idea of distance becomes especially interesting. When you see Orion in the sky, all of its stars appear equally present. Betelgeuse does not look hundreds of light years closer than the belt. Rigel does not look deeper in space than the nebula. Everything feels like it belongs to the same layer of the sky. This is because your eyes are not built to measure cosmic depth. They are built to measure distances across a room, across a field, across a street. Once you get beyond a certain range, everything flattens out. So the sky becomes a kind of depthless surface, even though it is anything but. This flattening is part of what makes the night sky feel intimate. You can look at a star that is hundreds of light years away and feel like it is part of your immediate surroundings. But behind that feeling is a reality that stretches far beyond the horizon of everyday experience. Now let us take a closer look at what it means to see something that far away. Because distance in space is not just about space. It is also about time. Light travels at a finite speed. It does not arrive instantly. So when you look at a star, you are seeing it as it was in the past. If a star is 100 light years away, you are seeing it as it was 100 years ago. If it is 1,000 light years away, you are seeing it as it was 1,000 years ago. So when you look at Orion, you are seeing a mix of different times layered together in a single view. Betelgeuse appears as it was several centuries ago. The belt stars appear as they were more than a millennium ago. The nebula appears as it was around the time when the first telescopes were being turned toward the sky. This means that Orion is not just a picture of a place. It is a collage of moments, a collection of different pasts arriving together in your present. Now, let us take this one step further, because this layering of time adds another dimension to the idea of up there. When you say up there, you might imagine a location, a point in space. But what you're actually seeing is a point in space and a point in time. You're looking at where a star was, not where it is now. This does not usually matter for everyday stargazing, because stars move slowly on human timescales. But on the scale of centuries and millennia, they do move. They drift through space. They change. They evolve. So the Orion you see tonight is not exactly the Orion that exists right now in the galaxy. It is a slightly younger version, a past arrangement, frozen in light. This gives up there a kind of gentle complexity. It is not just far away, it is also long ago. Now, let us think about how astronomers actually measure these distances, because the idea of hundreds and thousands of light years is not something you can determine by looking alone. For nearby stars, astronomers use a method called parallax. As the Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars. By measuring this tiny shift, astronomers can calculate how far away the star is. This works well for stars within a few thousand light years. For more distant objects, other methods come into play. Astronomers look at how bright a star appears compared to how bright it should be based on its type. They study the way stars move within clusters. They use relationships between certain kinds of variable stars and their intrinsic brightness. All of these techniques are ways of turning light into a ruler, of using the properties of stars themselves to measure the space between them and us. In the case of Orion, these methods have allowed astronomers to map the region in 3 dimensions, building a picture of where its stars and clouds actually sit in space. What they have found is that Orion is not a thin sheet of stars. It is a thick, extended region, a kind of stellar landscape that stretches across hundreds of light years in depth. So when you look at the belt, the nebula, the shoulders and the feet, you are looking into a volume of space, not just across a surface. Now, let us bring this back to the simple question of how far away up there feels. If you were to ask someone on the street how far away the stars are, they might say really far. And that answer, in its own way, is perfectly accurate. But what is interesting is how our sense of really far changes as we move through these layers of scale. The moon feels far until you think about the sun. The sun feels far until you think about the nearest stars. The nearest stars feel far until you think about Orion. Orion feels far until you think about the centre of the galaxy, which lies about 26,000 light-years away. The galaxy feels far until you think about other galaxies, millions of light-years away. At each step, the previous one becomes smaller by comparison. So up there is not a fixed distance. It is a moving boundary, one that recedes every time you take a step outward in understanding. Now, let us imagine a different kind of journey, one that does not involve travelling at all. Picture yourself standing still, on Earth, while the universe moves. The Earth rotates, turning the sky overhead. The Earth orbits the Sun, changing which stars are visible at night over the course of the year. The Sun orbits the centre of the Milky Way, carrying our entire solar system along a vast, slow path through the galaxy. As this happens, the Orion region is also moving, orbiting the galaxy in its own way, drifting relative to us over millions of years. So even the direction you point when you say up there is not fixed. It changes as the Earth and the galaxy move. This means that Orion, as a region of space, is not just far away. It is also in motion, part of a dynamic rotating system that spans tens of thousands of light years. Now let us return to the experience of looking at Orion one more time, because this is where all of these layers of distance come together in a single quiet moment. You tilt your head back, you find the belt, you trace the shoulders and the feet, you see the faint blur of the nebula. All of it fits comfortably into your field of view. In that moment you are connected, through nothing but light, to stars that are hundreds and thousands of light years away, to a region of the galaxy that is vast, layered and active. You do not need to feel the full weight of that scale. You do not need to hold all of those numbers in your mind. You can simply let the idea of distance sit quietly in the background, like a gentle hum. Because the beauty of stargazing is not in fully grasping how far away everything is. It is in knowing softly that up there is much larger, much deeper, and much more layered than it first appears. Beneath the simple outline of a hunter drawn in light, there is a quieter, wider place that does not announce itself at first glance. It does not shine with the brightness of Rigel, or glow with the warm colour of Betelgeuse. It does not form a neat line like the belt. Instead, it sits behind and around those familiar points, stretching outward into space as a kind of extended neighbourhood, a region where stars, clouds, and invisible structures share the same slow, drifting address in the Milky Way. This is the deeper Orion, the part you do not see when you trace the shape, but the part that gives that shape its true sense of size. When we talk about a neighbourhood on Earth, we usually imagine a cluster of houses, a few streets, maybe a park or a corner store. The distances feel human. You can walk from one end to the other in minutes. You recognise familiar faces, familiar buildings, familiar sounds. Orion's neighbourhood is nothing like that. Here, the houses are stars, the streets are vast lanes of empty space, and the distances between one place and another are measured not in steps or kilometres, but in light years. You could spend a lifetime travelling at the speed of our fastest spacecraft, and still not cross from one side of this region to the other. And yet, from Earth, this entire neighbourhood is compressed into a small patch of sky that fits comfortably between your outstretched hands. Let us begin to step into this deeper space, not by focusing on the brightest stars, but by widening our view. Around Orion's main figure lies a broader collection of stars that astronomers group together into what is called the Orion OB1 association. The letters O and B refer to types of stars, the hottest and most massive ones, stars that shine blue-white and burn through their fuel quickly. This association is not a tight cluster like the Pleiades. It is a loose family, a spread-out group of young, massive stars that formed from the same general cloud of gas millions of years ago and are now drifting apart. This family stretches across hundreds of light years. Some members sit closer to Earth, some farther away. Some are part of the familiar outline of the hunter, while others sit outside it, unnoticed by casual stargazers. To get a sense of how this looks in space, imagine a slow-moving school of fish in the ocean. From above it might look like a single shape, a single patch of motion. But if you were to swim through it, you would find individuals spread out in 3 dimensions, some closer, some farther, all moving in roughly the same direction, bound by a shared origin and a shared path. The Orion Association is like that, but on a galactic scale. Now let us talk about the clouds, because a stellar neighbourhood is not just made of stars, it's also made of what lies between them. The Orion Molecular Cloud Complex is one of the largest and closest star-forming regions to Earth. It is a massive structure of gas and dust, stretching for hundreds of light-years across space. This complex includes the famous Orion Nebula, but it also includes many other regions that are either faint, dark, or invisible to the naked eye. Some parts of these clouds glow softly because they are being lit by nearby hot stars. Other parts appear as dark patches, not because they're empty, but because they are so dense that they block the light of stars behind them. These dark regions are often where new stars are forming, hidden from view inside thick cocoons of dust. So when you look at Orion, you're not just seeing stars floating in empty space. You're seeing stars embedded in a complex environment, a kind of cosmic weather system made of gas, dust, radiation, and gravity. This environment is dynamic. It is changing, slowly but constantly. Clouds collapse, stars ignite, radiation pushes material away, and gravity pulls it back together. Over millions of years, the structure of this neighbourhood shifts and reshapes itself. Let us pause for a moment on the idea of millions of years, because it is easy to let that phrase drift past without really feeling it. A million years is such a long time that it is hard to connect to. Human history, as we usually think of it, only stretches back a few thousand years. Written language, cities, agriculture, all of these things are recent on that scale. But in Orion's neighbourhood, millions of years are like seasons. They are the rhythm of change. The stars you see in Orion today were born from clouds that began collapsing long before humans existed. The nebula you see now will be gone in a few million years, blown apart by the radiation and winds of the stars it helped create. New clouds will form elsewhere. New stars will be born. The neighbourhood will continue, but its details will change. Now let us take a step into how astronomers map this depth, because understanding Orion's hidden size requires more than just looking. For a long time, Orion was understood mostly as a two-dimensional picture, a shape on the sky. But in recent decades, missions like the Gaia spacecraft have begun to measure the distances to stars with incredible precision. By tracking the tiny shifts in a star's position as the Earth orbits the Sun, Gaia can calculate how far away that star is. With this data, astronomers can build three-dimensional maps of regions like Orion. These maps reveal something fascinating. The Orion region is not a flat sheet of stars and clouds. It is a long, twisted structure, more like a ribbon or a wave than a simple cluster. Some parts of the molecular clouds are closer to Earth, others are farther away, The entire complex appears to be bent and folded, possibly shaped by past supernova explosions, stellar winds, and the large-scale motion of the galaxy itself. So when you look at Orion's outline, you are actually looking at a projection of this long three-dimensional structure onto the sky. The shape you see is a kind of shadow cast by a much deeper, more complex form. Let us imagine this in a different way. Picture a long winding mountain range. From a distance, if you look at it from just the right angle, the peaks might line up, forming a simple silhouette. But if you were to fly over it, you would see valleys, ridges, bends, and layers of terrain stretching far into the distance. Orion's neighbourhood is like that. From Earth you see the silhouette. From a three-dimensional perspective you would see a landscape. Now let us step into that landscape and explore some of its features, even if only in imagination. Near the heart of the Orion Nebula is a group of young stars called the Trapezium Cluster. These stars are only a few million years old, which in stellar terms is very young. They shine intensely, and their radiation lights up the surrounding gas, making the nebula visible from Earth. Around them are disks of material, protoplanetary disks, swirling clouds of dust and gas that may one day form planets. Some of these disks have been imaged directly, appearing as dark silhouettes against the glowing background of the nebula. This means that within Orion's neighbourhood there are places where planetary systems are in the process of being built. Not finished worlds, not established orbits, but the raw ingredients of future solar systems slowly taking shape. Farther out, beyond the bright glow of the nebula, are regions where stars have already formed and moved on. These stars drift away from their birthplaces, carrying with them the chemical fingerprints of the clouds they were born from. Some of these stars may have planets, some may one day host life, some may burn quietly for billions of years, long after the current structure of Orion has changed beyond recognition. So the hidden depth of Orion's neighbourhood is not just a matter of distance, it is a matter of time, of past and future, of processes that stretch across eras. Now let us think about how this neighbourhood fits into the larger structure of the galaxy. The Milky Way is a spiral galaxy, with arms that wind outward from a dense central region. These arms are not solid structures, they are patterns of higher density, places where gas and stars tend to gather. The Orion region lies in a smaller arm or spur, sometimes called the Orion arm or the local arm. This is a region that includes our own solar system as well as many other star-forming areas. So Orion's neighbourhood is not isolated. It is part of a much larger network of regions, each one contributing to the overall structure of the galaxy. If you could zoom out far enough, you would see the Orion region as a small patch of brightness along one of the galaxy's sweeping arms, one ripple in a vast rotating disk of stars and clouds. This adds another layer to the idea of depth. Orion's hidden size is not just about how big it is on its own, it is also about how it fits into something even larger. Now, let's return to the experience of looking at Orion from Earth, because this is where all of these layers of structure come together in a single, simple view. You see a hunter, you see a belt, you see a shoulder and a foot. Perhaps you notice the faint blur of the nebula if the sky is dark enough. What you do not see is the long twisted ribbon of clouds stretching behind those points. You do not see the young stars embedded in dust, the older stars drifting away, the cavities carved by radiation, the shock waves from ancient supernovae that may have passed through this region millions of years ago. All of that is hidden in depth, folded into the line of sight, and yet knowing that it is there can change the way the simple shape feels. It can turn the hunter from a flat picture into a doorway, a way of looking into a layered, active part of the galaxy. Now, let us take a moment to think about motion again, because neighbourhoods, even cosmic ones, do not stand still. The stars in Orion's association are moving. They are not orbiting one another like planets around a sun. They are moving as a loose group, drifting through the galaxy. Over millions of years, this group will spread out. The shared origin will become harder to trace. The neighbourhood will dissolve into the general background of the Milky Way. This means that Orion's stellar neighbourhood, as a recognisable region, is temporary. It has a beginning, and it will have an end. The stars will remain, but the sense of a connected region will fade. This adds a gentle sense of impermanence to the view. The hunter in the sky feels eternal, but the neighbourhood that gives him depth is part of a long, slow cycle of formation and dispersal. Now, let us imagine, just for a moment, what it would be like to travel through this neighbourhood, not at the speed of light, but at a pace that allows you to notice the details. You drift past faint, distant stars, each one a sun with its own system of planets, perhaps orbiting unseen. You pass through thin clouds of gas so sparse that you would not feel them, but thick enough on a cosmic scale to form new stars over time. You move near glowing regions where young stars light up their surroundings, creating bright knots of colour and shadow. You pass dark lanes where dust blocks the light, hiding whatever is forming within. This is not a tidy, organised place. It is a patchwork, a mix of activity and quiet, of brightness and darkness, and it stretches on, far beyond the limits of the familiar pattern. Now, let us connect this back to the idea of size one more time, because the hidden depth of Orion's neighbourhood challenges a simple way of thinking about how big things are. When you look at a mountain, you can walk around it. You can see its sides, its base, its peak. When you look at a building, you can step back and see its full shape. With Orion, you cannot do that. You see one projection, one angle, one view. The true size is wrapped up in dimensions you cannot directly perceive. This makes Orion a kind of lesson in humility. It reminds you that what you see is not all that is there, that even the most familiar shapes can hide vast complex structures behind them. Now, let us bring this gently back to the present moment, to the simple act of listening and imagining. Perhaps you're picturing Orion now, not just as a figure in the sky, but as a wide, layered region, a stellar neighbourhood filled with stars at different stages of life, clouds in different states of collapse and dispersal, and light travelling across centuries of space. You do not need to hold all of these details in your mind at once. You can let them drift in and out, like stars appearing and disappearing as clouds pass in front of them. The important thing is the sense of depth, the feeling that behind the simple pattern lies something much larger. Just below the steady line of Orion's belt, there is a faint, almost hesitant glow that does not look quite like a star. It does not resolve into a sharp point, no matter how carefully you focus your eyes. Instead, it appears as a soft blur, a small patch of light that seems to hover in place, as if the sky itself has breathed out a quiet cloud. This is the Orion Nebula, and within this gentle smudge lies one of the most active and revealing regions of star formation that we can see from Earth. For many people, this is the first nebula they ever encounter, even if they do not realise what they are looking at. Under a dark sky, far from city lights, it can be seen without any equipment at all. Through binoculars, it grows into a glowing shape. Through a telescope, it transforms into a complex structure of bright arcs, dark lanes, and layered clouds, a kind of luminous landscape suspended in space. But even that view is only a surface impression. The true scale and significance of the Orion Nebula reach far beyond what any single glance can reveal. Let us begin by placing it in space, because this cradle of stars is not floating in isolation. It is part of the larger Orion molecular cloud complex, a vast network of gas and dust that stretches for hundreds of light years across our region of the Milky Way. The Orion Nebula itself sits about 300 light years away from Earth. That means the light you see from it tonight began its journey more than 1,000 years ago. It left this cloud of glowing gas at a time when human history looked very different, when medieval cities were just beginning to rise, when written records were still rare in many parts of the world. So from the very beginning, this nebula connects you to a deep past, even as it shows you a process that is still unfolding right now. Now, let us talk about what a nebula actually is, because the word can make it sound like a single, unified object, when in reality it is more like a region, a volume of space filled with material. The Orion Nebula is made primarily of hydrogen gas, with traces of helium and heavier elements mixed in. There is also a significant amount of dust, tiny solid particles that can block and scatter light. This material is not evenly spread out. It forms clumps, filaments, and layers. Some parts are dense and dark, hiding whatever lies behind them. Other parts are thin and glowing, lit up by the intense radiation of nearby stars. What makes the Orion Nebula especially interesting is that it is an active star-forming region. This means that within these clouds, gravity is pulling material together, slowly compressing it into denser and denser clumps. When one of these clumps becomes dense and hot enough at its core, nuclear fusion ignites and a new star is born. This process is not quick. It takes hundreds of thousands, sometimes millions of years. But in the Orion Nebula, it is happening in large numbers, making it one of the closest and most accessible places for us to study how stars come into existence. At the heart of the nebula is a small group of very young, very hot stars known as the Trapezium cluster. These stars are only a few million years old, which, in stellar terms, is barely more than infancy. These young stars shine with intense ultraviolet radiation. That radiation slams into the surrounding hydrogen gas, stripping electrons from atoms and causing the gas to glow. This is why the nebula is visible at all. Without these stars, the cloud would be mostly dark, a hidden patch of cold gas drifting quietly through space. So the Orion Nebula is not just a birthplace of stars, it is also lit from within by the stars it has already created. There is a kind of feedback loop at work. Stars form in the cloud. Those stars then light up and reshape the cloud, influencing where and how future stars can form. Now, let us take a closer look at what this region looks like in 3 dimensions. Because from Earth, it is easy to think of the nebula as a flat patch on the sky. In reality, the Orion Nebula is a vast 3-dimensional structure. It spans about 24 light-years across. That means light, moving at its incredible speed, takes nearly a quarter of a century to travel from one side of this cloud to the other. Within that volume there are layers of gas and dust at different depths. Some parts are closer to us, some farther away. Some parts are being pushed toward us by the radiation of young stars, while others are being pushed away. So when you look at the nebula through a telescope, the bright arcs and dark lanes you see are not just surface features. They are the overlapping outlines of structures at different depths, projected into a single, 2-dimensional view. To imagine this, picture looking at a thick fog lit by several bright lamps from inside. Some parts of the fog glow brightly. Other parts remain dark. Some layers overlap, creating patterns of light and shadow. The Orion Nebula is like that, but on a scale that dwarfs anything we experience on Earth. Now, let us talk about the stars that are being born here, because this is where the nebula truly earns its reputation as a cradle. Inside the Orion Nebula, astronomers have identified thousands of young stars, many of them still surrounded by disks of gas and dust. These disks are called protoplanetary disks, and they are the raw material from which planets can form. Some of these disks have been imaged directly. They appear as dark, circular shapes silhouetted against the glowing background of the nebula. Each one of those silhouettes represents a potential solar system in the making, a place where planets may one day orbit a newly formed star. These young stars vary widely in size and mass. Some are destined to become massive, luminous stars like those in Orion's belt. Others will become small, faint red dwarfs, stars that will burn quietly for trillions of years. So within this single cloud you have the beginnings of a wide range of stellar lives, all unfolding at the same time, all shaped by the same environment. Now, let us connect this to the idea of scale, because the nebula's role in Orion's size is not just about its physical dimensions. The Orion Nebula is a kind of focal point for the entire region. It is one of the places where the hidden depth of Orion becomes visible, where the three-dimensional structure of the stellar neighbourhood reveals itself through light and shadow. Behind the belt, the nebula marks a deeper layer of space. It sits farther away than Betelgeuse and Bellatrix, closer than some of the most distant belt stars. It occupies a middle ground in the depth of Orion's region. This layering means that when you look at Orion, you are looking past some stars to see the nebula, and looking past the nebula to see other stars beyond it. Your line of sight passes through multiple layers of the Orion environment, each one contributing something to the view. So the nebula is not just a feature inside the constellation. It is part of the depth of the constellation, a marker of how far back into space Orion really goes. Now, let us take a moment to think about what the Orion Nebula would look like if you could approach it. Not physically, but visually. Imagine drifting through space toward this glowing region. From a distance, it would look like a faint hazy patch. As you get closer, the structure would begin to resolve. You would see long curved arcs of glowing gas, dark pillars of dust, and bright knots where young stars are clustered. The light in this region would not come from a single source. It would come from many young stars, each one casting its own glow on the surrounding material. Some areas would be brightly lit, others would remain in shadow, creating a complex layered landscape of light and darkness. There would be no clear boundary where the nebula ends and empty space begins. The cloud would fade gradually into thinner and thinner gas, a soft transition from something to almost nothing. This lack of sharp edges is another reminder that the Orion Nebula is not an object in the way we usually think of objects. It is a region, a volume, a part of the galaxy where certain conditions happen to come together in a way that allows stars to form and light to shine. Now let us return to the idea of time, because the nebula is not just a place in space, it is a moment in a process. The Orion Nebula has not always looked the way it does now. In the past it was darker before the trapezium stars formed and began to light it up. In the future it will look different again. As the young stars in its core continue to shine, their radiation and stellar winds will push the surrounding gas and dust away. Over time, this will disperse the cloud, shutting down star formation in this region. In a few million years, the Orion Nebula will likely fade, leaving behind a cluster of stars where a glowing cloud once hung. So what you see tonight is a temporary stage in a long story, a snapshot of a process that spans millions of years. Now, let's think about how this fits into the larger scale of Orion's neighbourhood. The Orion Nebula is just one of many star-forming regions within the Orion molecular cloud complex. There are other nebulae, both glowing and dark, spread across this vast structure. Some of these regions are closer to Earth, some are farther away, some are more active, some are quieter. Together they form a kind of stellar landscape, a patch of the Milky Way where star formation is happening on a grand scale. So when you look at the Orion Nebula, you are not just looking at a single cradle. You are looking at one visible part of a much larger system of cradles, a network of places where stars are being born across hundreds of light years of space. Now, let us bring this back to the simple human experience of seeing that faint blur below the belt. It is easy to miss, especially under bright skies. It does not stand out the way the major stars do. You have to look for it. You have to let your eyes adjust. You have to give it a moment. And when you do, what you find is not just another point of light. You find a window into a process that shapes the entire galaxy. This small, soft glow represents the raw material of future stars and planets. It represents a place where gravity and radiation are locked in a slow, ongoing negotiation, deciding what will form and what will disperse. It represents, in a very real sense, the future of the night sky. The stars being born there now will one day drift away from their birthplace and become part of new patterns, new constellations, seen by beings who may not even call them by the same names we do. Now let's take a step back and connect this to the larger theme of Orion's size one more time. The Orion Nebula adds depth to the hunter's shape. It turns a simple outline into a layered view of a region where things are happening at different distances and different stages of time. It also adds scale in another way. It shows that Orion is not just a collection of stars, it is a place where stars come from. This makes the constellation feel less like a picture and more like a chapter in a much larger story, one that includes birth, change, and eventual dispersal. Now let us imagine how this might feel to someone in the distant future. Perhaps millions of years from now, the Orion Nebula will be gone, its gas dispersed, its stars scattered. The shape of Orion will have changed. The belt will no longer line up. The hunter will not look like a hunter anymore. But the stars that were born in this nebula will still exist, shining somewhere in the galaxy, part of other patterns, other stories. So this faint blur you can see tonight is a fleeting thing on a cosmic timescale. A brief moment when a cloud of gas happens to be glowing in just the right way, in just the right place, for you to notice it. Now let us return, gently, to where you are, perhaps listening in a quiet room, perhaps imagining the sky above. You do not need a telescope to appreciate the idea of the Orion Nebula. You only need to know that behind those three steady belt stars, there is a region of space where new stars are being born, where light and matter are shaping the future of the galaxy. That knowledge can sit quietly in the background, like a soft glow of its own. Across the small, familiar patch of sky where Orion stands, something invisible is always in motion. It does not shimmer. It does not leave a trail. It does not announce itself in any way you can sense directly. And yet, without it, none of the stars, none of the clouds, none of the glowing regions would ever reach you at all. That something is light, and in Orion's case, its journey is long enough to turn a simple drawing in the sky into a slow, ongoing conversation across years and centuries. From Earth, Orion feels compact. You can take in the entire figure in a single glance. Your eyes move from shoulder to belt to foot in seconds. It feels like a small thing, a manageable thing, a shape that fits neatly into your awareness. But now, let us step away from how it feels and begin to think about how long it actually takes for light to travel across that same shape in space. Because the distance between those points of light is not measured in the time it takes your eyes to move. It is measured in the time it takes light itself to cross the gaps between stars, clouds, and glowing regions. Let us begin with something close and familiar, because it helps anchor what comes next. When you turn on a lamp in a dark room, the light reaches the walls almost instantly. The room fills with brightness before you have time to notice the delay. Light at everyday distances feels infinite in speed. Even when you look at the moon, light only needs a little more than a second to travel from its surface to your eyes. You could clap your hands and the sound would take longer to reach you than the light from the moon takes to arrive. But Orion lives on a very different scale. The light from Betelgeuse, glowing warmly at the hunter's shoulder, has been travelling for hundreds of years before it meets your eyes. The light from Rigel, sharp and blue at the foot, has been travelling even longer. The light from the belt stars has been on the move for more than 1,000 years. That is already a remarkable idea on its own. But now, let us think about the space between those stars, not just the space between them and you. Because light does not only travel from Orion to Earth, it also travels within Orion's region, moving from star to star, from cloud to cloud, across the wide layered environment that makes up the hunter's true form. Imagine a beam of light leaving Betelgeuse and heading toward Rigel. It is not moving sideways across a flat picture. It is travelling through three-dimensional space, weaving through a vast volume filled with thin gas, scattered dust, faint stars, and invisible structures. That journey, from one end of Orion's familiar outline to the other, would take centuries. To make that more tangible, consider this. The distance between Betelgeuse and Rigel is on the order of several hundred light-years. That means if a pulse of light were to leave Betelgeuse today and head toward Rigel, it would not arrive for hundreds of years. In that time, entire generations of humans would be born and pass away. Languages would change, cities would rise and fall, technologies would advance in ways we cannot easily predict, and still, that light would be travelling, quietly crossing the space between 2 points that look, from Earth, like they're only a few inches apart in the sky. Now, let us think about the belt, because it sits between those two ends like a kind of bridge. The belt stars themselves are spread across a depth of nearly 1,000 light years. Light travelling from the nearest belt star to the farthest one would take centuries to complete that journey. So when you draw a line across the belt in your mind, you're drawing across a span of time as much as a span of space. The shape you see is not just a picture. It is a collection of light signals that left their sources at very different moments in history and are only now arriving together in your present. This means that Orion, as you see it, is not a single moment frozen in the sky. It is a layered image built from different times. Now let's explore that idea a little more deeply, because it has a quiet way of changing how you think about what it means to see something. When you look at a tree outside your window, you're seeing it almost as it is right now. Light leaves the tree and reaches your eyes in a fraction of a second. The delay is so small that, for all practical purposes, the tree and the image of the tree are the same moment. When you look at the moon, you are seeing it as it was a little over a second ago. That is still close enough to feel like now. But when you look at Orion, you're seeing a blend of thens. Betelgeuse appears as it was around the time of early telescopes. Rigel appears as it was before the first photographs were ever taken. Alnilam appears as it was when medieval societies were still shaping the world. And the Orion Nebula appears as it was when early scientific ideas about the universe were just beginning to take form. All of those moments are stacked together in your view, compressed into a single shape that feels like the present. So when light takes years to cross a drawing in the sky, it is not just crossing space, it is crossing history. Now, let us shift perspective slightly and think about what happens to light as it moves through Orion's region. Because that journey is not always simple or straight. Space is not completely empty. Even in the thin, sparse environment between stars, there are atoms, molecules, and tiny grains of dust. Over long distances, these small things can have a noticeable effect on light. Some light is absorbed by dust, some is scattered, changing its direction slightly. Some is reddened, shifting toward longer wavelengths as it passes through clouds. This means that the light you see from Orion has been shaped by the space it travelled through. It is not just a direct message from a star to your eyes. It is a message that has passed through a medium, one that has left subtle marks on it. In the Orion Nebula, this effect is especially dramatic. The glowing gas you see is light from young stars interacting with the surrounding material. The dark lanes you see are places where dust blocks light from behind, creating shadows on a cosmic scale. So within Orion, light is not just a traveller, it is also a sculptor. It shapes what you see by interacting with the environment it moves through. Now, let us think about how long it takes light to cross the nebula itself. The Orion Nebula is about 24 light years across. That means light needs 24 years to travel from one side of it to the other. So if a new star were to suddenly ignite on one edge of the nebula, the glow from that event would take decades to reach the far side of the cloud. This means that even within this single glowing region, different parts of the nebula are seeing different moments of the same event at different times. The nebula is, in a sense, a place where time itself is spread out across space. Now, let us widen the view again and consider the entire Orion region. From one edge of the Orion molecular cloud complex to the other, light would take hundreds of years to travel. So when you think about Orion as a neighbourhood, it is not a place where information moves quickly. It is a place where messages take centuries to pass from one end to the other. This adds a quiet, slow rhythm to the region. Changes do not ripple through instantly. They move at the speed of light, which, on this scale, feels almost leisurely. Now, let us bring this back to the act of looking up, because this is where the idea of light's journey becomes personal. When you see a star twinkle, you're not seeing the star itself flicker. You are seeing Earth's atmosphere shift and move, bending the path of the light as it passes through. The star's light has already travelled for hundreds or thousands of years through space, only to be nudged and distorted in the last few kilometres of its journey. So in that tiny flicker, you're seeing the final step of a long voyage, a small interaction between a beam of ancient light and the thin layer of air around your planet. Now, let us think about what it means for Orion to be a drawing in the sky in this context. A drawing, on paper, is static. All of its lines exist at the same time. They do not have a history. They do not move or change unless you erase or redraw them. Orion's drawing is different. Each line in the shape is made of light that left its source at a different time. The shoulders, the belt, the feet, the nebula, all of them are messages from different moments in the past arriving together in your present. This means that Orion is not a snapshot. It is a collage. Now let us explore what that implies for change, because Orion is not frozen in time, even if it looks that way to us. Betelgeuse is a variable star. It changes in brightness and size over time. Rigel will change as it evolves. The stars in the nebula are forming and emerging from their dusty cocoons. All of these changes are happening now, in the present moment of the galaxy, but you are not seeing them as they happen. You are seeing them as they were. So there is always a delay, a gap between the event and your awareness of it. This gap is not something to be frustrated by. It is something to appreciate, because it gives you a kind of built-in connection to the past. Every time you look at Orion, you are looking at history written in light. Now let us take a small step into a more speculative kind of imagining, because it can help make this idea feel more concrete. Picture a signal, like a flash of light, being sent from one side of Orion's region to the other. Perhaps it is a natural event, like a supernova, a massive star exploding and releasing an enormous burst of light. That light begins its journey, racing outward in all directions. It passes through clouds, through star systems, through empty space. After hundreds of years, it reaches the far side of the region. Then, after more hundreds of years, it reaches Earth. So by the time you see that flash in the sky, it has already crossed Orion and then crossed the space between Orion and you. This means that a single event in Orion can take 1,000 years or more to fully reveal itself across the region and to distant observers. So even dramatic changes unfold slowly, stretched out across space and time. Now let us bring this back to something simpler, because sometimes scale is easier to feel in small steps. Think about the distance between you and a friend on the other side of a large city. You can send a message, and it arrives almost instantly. The delay is so small that you hardly notice it. Now, think about sending a message across a continent. There is a noticeable delay, but it is still measured in fractions of a second. Now think about sending a message across the solar system. The delay becomes minutes or hours. Now think about sending a message across Orion. The delay becomes centuries. This is the scale we are dealing with. So when light takes years to cross a drawing in the sky, it is not just a poetic idea. It is a literal description of how space works in this region. Now, let us return to the Orion Nebula for a moment, because it offers a particularly vivid example of this layered time. The young stars in the trapezium cluster light up the surrounding gas. The light from those stars travels outward, illuminating different parts of the nebula at different times. So the bright arcs you see are not all being lit up simultaneously. They are being lit up as the light reaches them. This means that the nebula itself is, in a subtle way, a record of light's journey, a map of where and when radiation has reached different parts of the cloud. Now let's consider how astronomers use this idea to learn about the structure of Orion. By studying how light from stars is absorbed or scattered by the clouds, astronomers can infer where those clouds are in three-dimensional space. They can see which stars are in front of which clouds, which parts of the nebula are closer or farther away. In this way, light becomes a tool, not just a messenger. It carries information not only about its source, but about everything it passes through. So when you look at Orion, you're not just receiving light from stars. You're receiving light that has interacted with the entire region, carrying with it clues about the structure and depth of the neighbourhood. Now let us bring this back to the idea of the drawing one more time. A drawing suggests something simple, something finished. But Orion's drawing is never finished. It is always being updated, always being revised, one beam of light at a time. As stars evolve, as clouds shift, as new stars are born and old ones fade, the messages they send out change. Those changes take time to reach you. So the Orion you see tonight is a version of Orion that exists only in your sky, a version built from light that left at different times and travelled across different paths. Tomorrow night you will see almost the same shape, because the changes are slow, but it will not be exactly the same, because light will have moved on, a new light will have arrived. Now, let us think about how this connects to your own sense of time, because this is where the cosmic scale can quietly touch the human one. Your day is measured in hours, your year is measured in months, your life is measured in decades. Orion's changes are measured in thousands and millions of years. But when you look at the sky, all of that difference in scale collapses into a single moment of seeing. You and a star that is thousands of light years away meet in the same instant, connected by a beam of light that has been travelling for most of human history. That is a kind of quiet connection that does not require any effort or understanding. It simply happens every time you look up. Now, let us take one last step outward in this section, because the idea of light's journey does not stop at Orion. The Milky Way is filled with regions like this, where light takes years, centuries or millennia to cross from one part to another. Beyond the Milky Way, in other galaxies, the distances are even larger. Light takes tens of thousands of years to cross a single galaxy. It takes millions of years to travel between galaxies. So the idea of light taking years to cross a drawing in the sky is just one layer in a much larger pattern, one that extends across the entire universe. But for now, we can let our attention rest here, within the familiar shape of the hunter, where the scale is already large enough to gently stretch the imagination. The next time you find Orion above you, you might let your eyes trace the familiar lines again, from shoulder to belt to foot. And as you do, you might carry quietly in the back of your mind the idea that those simple lines are made of journeys, each one taking years, centuries, or more to reach you. The drawing in the sky is not drawn with ink, it is drawn with time. Imagine for a moment that you're not standing on Earth at all. There is no familiar horizon, no sense of gravity holding your feet to the ground, no sky above and no ground below. Instead, you're suspended in open space, surrounded on all sides by a deep, quiet field of stars. The Milky Way no longer arches overhead as a glowing band. It stretches out around you in every direction, a vast layered disk of light and shadow. From this place, you turn slowly, searching for something familiar. Somewhere out there, in the enormous spread of the galaxy, lies the region we call Orion. But from here, it does not announce itself as a hunter, a belt, or a recognizable figure. It is just another patch of space, another collection of stars and clouds among billions of others. This is where the idea of Orion begins to change in a fundamental way. On Earth, Orion feels like a fixed landmark. It rises and sets. It returns with the seasons. It holds its shape, steady and reliable. But from somewhere else in the galaxy, Orion is not a picture. It is a place, and even that place is not neatly defined. Let us begin by placing yourself somewhere specific, because somewhere else in the galaxy can mean an enormous range of locations. Imagine drifting a few hundred light years to the side of the Orion region, far enough that you're no longer lined up with the familiar alignment of its stars. You're still within the same spiral arm of the Milky Way, still in roughly the same galactic neighbourhood, but your angle of view has shifted. From here, you look back toward where Earth would be. The stars that once formed Orion's belt no longer line up. Instead of a straight row of 3 points, you see a loose scattering. One star sits closer to you, glowing more brightly. Another lies farther away, dimmer and smaller. The third is offset to the side, no longer forming a clean line with the others. Betelgeuse and Rigel, which once marked the warm shoulder and the sharp blue foot of the hunter, now appear as just 2 bright stars among many. They no longer sit at the ends of a figure. They simply occupy their own places in space. The Orion Nebula, which once hung beneath the belt as a faint blur, now spreads out into a wide layered cloud. From this angle you might see its shape more clearly, its folds and cavities and glowing regions no longer flattened into a small patch, but extended into a 3-dimensional form. So the first thing that happens when you leave Earth's point of view is that Orion stops being a drawing. It becomes a loose, irregular region of stars and clouds, without sharp edges, without a clear outline, without a simple story attached to its shape. Now, let us move a little farther, because a few hundred light years is still close, in galactic terms. Imagine travelling a few thousand light years away, perhaps toward the inner part of the Milky Way, closer to the dense, bright centre of the galaxy. From here, you turn and look back toward the outer regions where our Sun and Orion reside. The sky looks different here. The background is much brighter. The density of stars increases. The Milky Way's core glows with a thick, luminous presence, filling a large portion of your view. In this crowded star field, the Orion region does not stand out as something special. It blends in with countless other clusters, clouds, and associations. You might notice a patch of blue-white stars, a faint glowing cloud, a region of activity. But it would not form a hunter. It would not form a belt. It would not carry the same visual weight it does from Earth. This shift in prominence is another quiet lesson in scale and perspective. Orion feels important to us because of where we stand. It is bright, close, and well positioned in our sky. But in the vastness of the Milky Way, it is one of many such regions, one thread in a much larger tapestry. Now let us take this a step further and imagine viewing Orion from a completely different part of the galaxy, perhaps from the opposite side of the Milky Way's disk. From there, the distance back to Orion might be tens of thousands of light years. The light you see from that region would have left long before modern humans existed. The Orion you would be seeing would be a very young version of the region, perhaps before some of its current stars had even formed. From that distance, Orion would not be a constellation at all. It would be a faint, barely noticeable patch of light among the countless stars of the galaxy's disk. The idea of a hunter, a belt, a shoulder, and a foot would not exist. This brings us to an important realization. Orion is not something the universe made. Orion is something we made. The stars are real, the clouds are real, the distances are real, but the shape, the story, the figure, all of that exists only because of a specific point of view on a small planet orbiting a modest star in one particular corner of the galaxy. Now, let us explore what it would feel like to see Orion from a truly alien perspective, one that is not just far away, but fundamentally different. Imagine a planet orbiting a star within the Orion region itself, perhaps inside one of the stellar associations or near the edge of the molecular clouds. From that planet's surface, the sky would look entirely different. Some of the stars that we see as distant points would appear much brighter and larger. Betelgeuse might dominate the sky, a massive reddish presence far brighter than any star in our own sky. The belt stars, if you could see them at all, would be scattered across different parts of the heavens, no longer forming a line. The Orion Nebula might fill a significant portion of the sky. a glowing, structured cloud of light and shadow, perhaps bright enough to cast faint illumination across the planet's surface. From this place, the idea of Orion as a single region might not even make sense. The neighbourhood would be the sky. The stars we group together would be part of a much larger, more immediate environment. This highlights another layer of perspective. Constellations are not just about where you are in the galaxy. They're also about what is close to you. From Earth, Orion stands out because its major stars are relatively nearby and bright. From somewhere else, a different group of stars might take on that role, forming a new, familiar pattern for whoever is looking up. Now let us think about how this connects to the idea of navigation and orientation, because for a long time, humans used the stars as a way to find their place in the world. On Earth, Orion can help you find directions. Its belt can point you towards Sirius or Aldebaran. Its position in the sky can help you estimate the season. But in the galaxy, there is no up or down, no north or south in the same sense. Orientation becomes a matter of reference points, of choosing landmarks among a sea of stars. From another location in the Milky Way, Orion would not be a landmark. Something else would be. Perhaps a dense star cluster would stand out. Perhaps a bright nebula. Perhaps the glowing core of the galaxy itself would dominate the sky, acting as a central point of reference. So Orion's role as a guide is not universal, it is local. Now, let us explore what astronomers actually do when they try to see Orion from somewhere else. Because while we cannot physically travel to different parts of the galaxy, we can simulate different perspectives. Using three-dimensional maps built from distance measurements, astronomers can create models of regions like Orion, and then view them from different angles. They can rotate the model, shift the viewpoint, and see how the arrangement of stars and clouds changes. When they do this, the familiar shape disappears almost immediately. The belt bends, the shoulders drift, the nebula stretches into a long, uneven structure. The region becomes something more like a cloud of points than a figure. This kind of modelling reveals something important. The stars in Orion are not arranged in a way that suggests any natural physical shape. They are arranged by chance, by the random distribution of star formation within a cloud. The hunter exists because of us, not because of them. Now let's imagine taking this idea even further. Beyond the Milky Way, picture yourself in another galaxy, looking back at our own from millions of light years away. The Milky Way appears as a faint glowing spiral, a soft swirl of light in the darkness. From there, Orion is completely invisible as a distinct region. It is just one tiny part of one faint arm of one distant galaxy. This is a humbling shift in scale. The figure that feels so large and important in our sky becomes a detail too small to notice from a truly distant perspective. And yet, from Earth, that same figure can feel vast, layered, and full of meaning. This contrast is one of the quiet wonders of perspective. Size and importance are not fixed qualities, they depend on where you stand. Now, let us return to the idea of what Orion actually is in physical terms, because this remains true no matter where you look from. Orion is a region of space filled with stars, gas and dust. It is part of a larger structure within the Milky Way, a segment of a spiral arm where star formation has been active for millions of years. That reality does not change with perspective. What changes is how that reality is arranged in your view. From Earth, it is a hunter. From nearby in the galaxy, it is a loose association. From far away, it is a faint patch in a spiral arm. From outside the galaxy, it is an invisible detail in a distant swirl of light. All of these are true at the same time. Now, let us bring this back to a more personal level, because this idea of shifting perspective can quietly connect to how we experience our own place in the world. On Earth, your surroundings feel immediate and important. Your city, your region, your country, all of these feel like large defining spaces. But from space, the Earth becomes a small blue dot. From farther away, it becomes a pale point of light. From outside the solar system, it disappears into the general glow of the sun. In a similar way, Orion feels large and defining from Earth, but from elsewhere, it fades into the background of something much bigger. This does not make it less meaningful. It simply places it within a larger context. Now, let us imagine, just for a moment, what it would be like to meet another observer somewhere else in the galaxy, someone who looks up at their own sky and sees a completely different set of patterns. Perhaps their Orion is a cluster of stars near the galactic centre, forming a shape that has no meaning to us. Perhaps they have their own stories, their own names, their own ways of connecting with the sky. If you could compare notes, you would find that the same stars you see as part of Orion might be part of a completely different pattern in their sky, or might not stand out at all. This highlights something quietly beautiful about constellations. They are a way for a place to leave its mark on the sky. They tell you as much about the observer as they do about the stars. Now let us return to the Orion region one more time, but from a slightly different imagined viewpoint. Picture yourself not on a planet, but floating in open space within the Orion molecular cloud complex, perhaps near the edge of the Orion Nebula. From here, the sky's filled with glowing gas and bright young stars. The light is not gentle, it is intense, scattered, coloured by the clouds around you. The Milky Way as a band might be hard to distinguish, because you're inside one of its active regions. From this perspective, Earth's sky, with its dark background and isolated bright stars, would feel empty and sparse. This inversion of experience is another reminder that what feels rich or empty, large or small, depends on where you are. Now let us gently bring this back to the idea of size one more time, because seeing Orion from somewhere else changes not just how it looks, but how it feels. From Earth, Orion feels like a big figure spanning a wide patch of sky. From elsewhere, it might feel like a small cluster, or a distant blur, or nothing special at all. But in physical terms, it remains the same region, the same collection of stars and clouds, the same stretch of space. So size, in this sense, is not just about physical dimensions, it is about perception. Now let us return softly to where you are, listening, perhaps imagining the sky above. From here, Orion still rises, still forms its familiar shape, still offers its belt, its shoulder, its foot. You do not need to abandon that view in order to appreciate the others. You can hold both at once. Orion as a hunter in the sky, Orion as a loose region of the galaxy, Orion as a faint patch in a distant spiral arm. Each one is a different layer of the same reality. Instead of picturing Orion as a flat shape pinned to the sky, try letting it loosen, as if the familiar outline were gently pulled away from the surface of the night and allowed to float outward into depth. The hunter's shoulders, belt, and feet no longer sit on the same invisible plane. They begin to drift forward and backward, separating into layers, each one occupying its own place in a wide, open volume of space. In that moment, Orion stops being a picture and starts becoming a place. From Earth, your eyes naturally compress everything into a single surface. The sky feels like a dome, a curved ceiling where stars are attached like distant lights. This way of seeing is comfortable. It makes the universe feel organised and contained. But space does not work like that. Space is not a backdrop. It is the main stage. Every star in Orion sits at a different distance from you. Every cloud of gas and dust occupies its own region, its own depth. When you allow yourself to imagine that depth, this size of Orion expands in a way that is hard to hold all at once. Let us begin with something simple and build from there. Imagine you could place markers in space at the positions of Orion's most familiar stars. One marker for Betelgeuse, one for Rigel, one for each of the belt stars, one for the Orion Nebula. Now imagine connecting those markers, not with lines drawn on a flat surface, but with lines floating in open space. What you would get is not a stick figure. You would get a wide, irregular, three-dimensional arrangement, with some markers much closer to you and others far deeper into the galaxy. Betelgeuse, at around 600 to 700 light-years away, would sit in front of much of the rest of the region. Rigel, at roughly 860 light-years, would sit farther back. Alnilam, one of the belt stars, would be far deeper still, nearly 2,000 light-years away. The Orion Nebula would occupy a middle layer, around 1,300 light-years out. So the body of Orion, when you think of it in 3 dimensions, is not a thin sheet. It is a deep structure that stretches across more than 1,000 light-years from front to back. To give that some context, light takes more than 1,000 years to travel from the nearest part of Orion's main figure to the farthest. That means if you could somehow send a beam of light from Betelgeuse toward Alnilam, it would be travelling long after every person alive today had been replaced by generations yet to come. This is the depth hidden behind a shape that fits neatly into your field of view. Now, let us take a step further and imagine what it would be like to move through this space. Not just measure it. Picture yourself starting near Betelgeuse, floating in the thin, sparse environment around that massive glowing star. The light is warm and intense, the star's presence dominating the region. From there, you begin to drift inward, away from Earth's side of Orion and deeper into the region. The star behind you slowly shrinks in your view, becoming just another point of light among many. Ahead of you, other stars and faint clouds begin to appear, scattered through the darkness. You pass through regions where the space between stars feels almost empty, where there are only a few distant points of light and a faint haze of gas. Then you move into areas where the environment becomes more active, where clouds of dust and gas thicken, where young stars glow and illuminate their surroundings. At some point in this journey you would cross the region of the Orion Nebula. You would move through glowing arcs of gas and dark, dense pockets of dust, passing near clusters of young stars surrounded by swirling disks of material. And then, beyond that, you would continue on, moving toward the deeper layers of the belt stars, eventually reaching Alnilam, far back in the Orion region, shining with immense power in a part of space that feels distant even from within Orion itself. This is not a short trip. Even in imagination, it is a journey across centuries of light travel. Now, let us pause and think about what this kind of size means in more familiar terms. On Earth, when we think about something being big, we usually think in terms of physical reach. A mountain is big because it towers over the land. An ocean is big because it stretches beyond the horizon. A city is big because it takes time to cross. Orion's size is different. You cannot walk across it. You cannot see its edges from a single vantage point. You cannot even meaningfully picture its full extent without stepping into abstraction. Its size is measured in the time it takes light to move, in the way different parts of it belong to different eras of history when their light reaches you. So when space turns three-dimensional, big stops being about physical presence and starts being about duration and separation. Now let us consider the Orion region not just as a collection of famous stars and a nebula, but as part of a larger structure within the Milky Way. Orion is embedded in the Orion Molecular Cloud Complex, a massive system of gas and dust that stretches for hundreds of light-years across space. This complex is not a simple blob. It is a network of filaments, sheets and clumps, shaped by gravity, radiation and past explosions of massive stars. This network forms a kind of backbone for the region, a framework within which stars form, evolve and drift away. So when you think about Orion in 3 dimensions, you're not just thinking about the stars you can name. You're thinking about a vast, invisible structure that holds them together. At least for a while. This structure itself is not still. It moves, it changes, it stretches and compresses as it orbits the centre of the galaxy and responds to forces from nearby regions. So Orion's 3-dimensional shape is not fixed. It is more like a slow-moving wave, shifting and evolving over millions of years. Now let us explore how astronomers actually visualize this. because while we're imagining drifting through space, scientists are building maps that try to capture this same sense of depth. Using precise measurements of stellar distances, motion and brightness, astronomers can create three-dimensional models of regions like Orion. These models show that the molecular cloud complex is bent and folded, forming a long curved structure rather than a simple straight one. Some parts of the cloud are closer to Earth, others are farther away. The entire system appears to be shaped by large-scale forces, possibly including shock waves from ancient supernovae and the overall motion of the Milky Way's spiral arms. So when space turns three-dimensional in a scientific sense, Orion becomes less like a cluster and more like a landscape. There are ridges of dense gas where star formation is active. There are valleys of thinner material where stars drift freely. There are bright regions carved out by radiation, and dark regions where dust blocks light. This landscape extends far beyond the boundaries of the familiar constellation shape. Now, let us think about how this changes the idea of inside and outside. From Earth, you might think of the Orion Nebula as being inside Orion, as a feature contained within the hunter's outline. But in 3 dimensions, the nebula is not inside anything. It is part of a continuous structure that extends in many directions. The idea of a boundary only exists in projection, in the way the region appears on the sky. In space, there is no clear line where Orion ends and the rest of the Milky Way begins. The density of stars and clouds simply changes gradually, fading from one region into another. So when you imagine Orion as a volume, it becomes less like a container and more like a gradient, a place where certain conditions are more common, but not exclusive. Now let us bring this back to the experience of scale one more time, because this is where three-dimensional thinking really changes how big Orion feels. If you look at Orion and measure its width on the sky, you might say it spans about 20 degrees, roughly the width of your hand held at arm's length. That is a comfortable, human-sized measurement. But if you measure Orion in depth, you are talking about a region that stretches more than 1,000 light-years. So the ratio between its apparent size and its true size is enormous. This is like looking at a distant mountain range and thinking it is a single ridge, only to discover that it actually extends for hundreds of kilometers into the distance, with multiple layers of peaks and valleys hidden behind one another. The difference is that in Orion's case, the hidden layers are not just kilometers away, they are centuries of light travel away. Now, let us imagine what it would be like to stand at one edge of Orion's region and look across it. Perhaps you are near the part of the molecular cloud closest to Earth. From there you look outward, deeper into the region. In front of you, you see stars scattered through space, some bright and massive, some small and faint. You see clouds of gas and dust, some glowing, some dark. You see empty stretches where there is very little at all. As you look farther and farther, the stars become more crowded, then more sparse, then more crowded again, depending on how the structure is arranged along your line of sight. The sense of distance becomes layered. You do not see a single far edge. You see a series of depths, each one fading into the next. This is what makes three-dimensional space so different from a flat picture. There is no clear boundary. There is always more behind what you can see. Now let us connect this to the idea of time again, because in 3 dimensions, distance and time are always linked. The farther away something is, the farther back in time you're seeing it. So as you look deeper into Orion's region, you're also looking further into its past. The front layers of the region appear as they were hundreds of years ago. The back layers appear as they were thousands of years ago. So Orion's 3-dimensional shape is also a 3-dimensional timeline. Different parts of it are frozen at different moments in their history, all presented to you at once. This means that when you imagine drifting through Orion, you are not just moving through space. You're also moving through time. Now let us think about what this implies for change and evolution within the region. Some stars you see in Orion today may already be gone in the present moment of the galaxy. They may have exploded as supernovae, leaving behind neutron stars or black holes. Some clouds you see glowing today may have already been dispersed by radiation and stellar winds. Some young stars you see emerging from the nebula may already have formed planets around them. All of these changes are happening now, but you are seeing them as they were. So Orion, in 3 dimensions, is not just big. It is layered with moments, with stages of development, with different parts of its story unfolding at different times. Now let us take a step back and think about how this 3-dimensional view changes the meaning of the word constellation. A constellation, by definition, is a pattern on the sky, a way of dividing up the celestial sphere into recognizable shapes. But Orion, in 3 dimensions, is not a pattern. It is a region. It is a place where stars form, evolve, and move on. It is a segment of the Milky Way with its own history and its own future. So when space turns 3-dimensional, Orion stops being a symbol and starts being a system. Now, let us consider what this might feel like emotionally, because sometimes scale is not just an intellectual idea, it is something you sense. There is a certain feeling that comes from realizing that the simple shape you learned as a child hides a volume of space so large that light itself takes centuries to cross it. It can make the night sky feel deeper, less like a ceiling and more like an opening. It can make the idea of up feel less like a direction, and more like a vast expanse you could fall into, endlessly. Now, let us imagine one more journey, because sometimes movement helps anchor these ideas. Picture a slow, steady path that begins at the very front edge of the Orion region, near the stars closest to Earth. You move inward, crossing layer after layer of space. You pass Betelgeuse's region, then move deeper toward the nebula, then deeper still toward the far belt stars. Each step, measured in hundreds of light years, takes you into a part of Orion that is not just farther away, but also farther back in time. Eventually you reach the deepest visible layers of the region, where the stars you see are ancient messages from a past that predates much of human history. At that point, you might look back toward Earth and realize that from here, the sun itself would be just another star lost in the background. This reversal of perspective is another way to feel how big Orion really becomes when you let go of the flat picture. Now let us bring this gently back to the present, because you do not need to travel in imagination across thousands of light years to appreciate this depth. You can simply look at Orion and remember that each point of light sits at a different distance, in a different layer of space, in a different moment of time. That awareness alone can turn a familiar shape into a vast layered volume. Long before any human ever looked up and traced a hunter across the stars, the points of light we now call Orion were already on the move. They did not begin their journey in a fixed pattern, and they will not end it that way either. The shape feels steady because our lives are brief. The sky feels still because our time is short. But across the long, quiet span of cosmic time, Orion is drifting, stretching, and slowly becoming something else. To begin understanding this, it helps to let go of the idea that stars are anchored in place. Every star in the sky is moving. Some move faster, some move more slowly, some travel in wide arcs around the centre of the galaxy. Others follow slightly different paths, influenced by the gravitational pull of nearby stars, clouds, and larger structures. Our own sun is moving too. It orbits the centre of the Milky Way at a speed of about 220 kilometres per second. That sounds fast, but the galaxy is so large that it still takes the sun more than 200 million years to complete a single orbit. Orion's stars are part of this same vast rotation. They're all being carried along by the slow, sweeping motion of the galaxy's disk. But on top of that shared motion, each star also has its own individual path, its own small drift relative to the others. This combination of shared movement and individual wandering is what slowly reshapes the familiar patterns in the sky. Let us begin by thinking about what motion in space really looks like, because it is very different from motion on Earth. On Earth, when something moves, you usually see it change position against a fixed background. A car drives past a building. A bird crosses the sky. The background stays still while the object moves. In space, there is no truly fixed background. Everything is moving. So the motion of a star is not just about where it is going. It is about how its path compares to the paths of all the other stars around it. This is why astronomers talk about something called proper motion, which is the slow, sideways movement of a star across the sky relative to more distant stars. For most stars, this motion is so small that you would not notice it over a human lifetime, but over thousands of years it becomes visible. Over tens of thousands of years it becomes dramatic. Now let us apply this idea to Orion. The stars that make up Orion's familiar shape are not a tightly bound cluster. They did not form in a single compact group that is still held together by gravity. Instead, many of them are part of a loose association, a group of stars that formed from the same broad cloud of gas but are now drifting apart. This means that from the moment they were born, Orion's stars were already on paths that would eventually separate them. They started out closer together, embedded in dense clouds of gas and dust. Over time, as those clouds were dispersed by radiation and stellar winds, the stars were released into the wider galaxy. Once free, they continued moving, each one following its own orbit around the galactic centre. So the Orion you see today is not the Orion that existed millions of years ago, and it will not be the Orion that exists millions of years from now. It is a momentary arrangement, a snapshot in a long, slow dance. Now, let us take a step back in time and imagine what Orion might have looked like in the distant past. If you could travel back a few 100,000 years, you would still recognise the general shape. The changes would be subtle, the belt would still line up, the shoulders and feet would still feel familiar. But if you go back a few million years, the differences would start to become noticeable. Some of the stars that are bright today might not have been visible yet. Others might have been closer together, forming tighter groupings. The nebula might have been darker, less lit before the young stars at its core had fully ignited. Go back tens of millions of years, and the entire region would look very different. Some of the massive stars we see today would not have existed yet. Others might have already lived and died, exploding as supernovae, and leaving behind remnants that are now drifting invisibly through space. The Orion molecular cloud complex itself might have been in an earlier stage of collapse, a vast cold structure just beginning to form stars. So the shape of Orion, as a recognisable figure, is a very recent thing on a cosmic timescale. Now, let us move forward in time instead. Imagine a few 100,000 years into the future. From Earth, if humans are still here to look up, Orion would look almost the same. The changes would be too small to notice easily, but over 1,000,000 years the differences would start to add up. The belt stars would no longer line up quite as neatly. The angles between the shoulders and the feet would shift. The figure would begin to stretch and skew. Over several million years, the hunter would become hard to recognise at all. The stars would have drifted far enough apart that the original pattern would dissolve into a scattering of points that no longer suggest a single, coherent shape. This is not because something dramatic happens all at once. It is because small motions, repeated over long periods of time, add up to big changes. Now, let us think about how fast these stars are actually moving, because this can help make the idea of slow drift more concrete. Many stars in our part of the galaxy move at speeds of tens of kilometers per second relative to one another. That is fast by everyday standards. A car on a highway moves at about 30 meters per second. A star moving at 30 kilometers per second is moving 1,000 times faster than that. But space is so large that even at those speeds it takes a very long time to cover significant distances. In 1 year, a star moving at 30 kilometers per second travels about 1 billion kilometers. That sounds enormous, but a light year is about 9 trillion kilometers. So at that speed, it would take a star about 9,000 years to move just 1 light year. Now remember that the depth of Orion's region is more than 1,000 light years. So when we talk about stars drifting across Orion's neighbourhood, we're talking about movements that unfold over millions of years. This is why the sky feels stable. The motion is real, but it is slow on human timescales. Now, let us think about how astronomers actually see this drift, because it is not something you can detect by simply watching the sky. By comparing precise measurements of star positions taken decades or centuries apart, astronomers can detect tiny shifts in where stars appear in the sky. These shifts are incredibly small, often measured in fractions of an arcsecond, which is a tiny angle, much smaller than anything your eye can resolve. But with careful instruments and long-term observations, these movements become clear. When astronomers map the proper motion of Orion's stars, they can see that many of them are moving away from the central regions of the association, spreading out like a slow-motion ripple. This supports the idea that Orion's stars were born together and are now dispersing into the wider galaxy. So the Hunter is not just drifting as a whole, it is gently coming apart. Now let us bring this back to the Orion Nebula, because this region adds another layer to the story of motion. The nebula is not still either. The gas and dust within it are moving, pushed by the radiation and stellar winds of the young stars inside. Some parts of the cloud are expanding outward. Other parts are collapsing inward to form new stars. So within this single region, you have both dispersal and creation happening at the same time. Stars are being born, even as older stars are drifting away. This creates a kind of slow, continuous flow, where the neighbourhood changes its membership over millions of years. Now, let us think about what happens to stars that leave Orion's region. Once they drift far enough away, they become part of the general background of the Milky Way. They mix in with stars from other regions, other associations, other birthplaces. Over time, it becomes impossible to tell where they came from, unless you study their motion and chemical composition in detail. So Orion stars do not stay Orion stars forever. They become part of the galaxy at large. This means that Orion, as a distinct neighbourhood, has a limited lifetime. It forms, it exists for a while as a recognisable region, then it dissolves. This is not unique to Orion. It is how star-forming regions across the galaxy behave. They are like temporary gatherings coming together for a while before their members drift apart. Now let us return to the idea of shape one more time, because this slow drift has a very direct effect on what you see in the sky. The constellations we know today are not the constellations that ancient humans saw tens of thousands of years ago, and they will not be the constellations that future humans see tens of thousands of years from now. For example, the North Star has not always been the North Star. Thousands of years ago, a different star filled that role. Thousands of years from now, another one will take its place. In the same way, Orion's shape has changed and will continue to change. If you could compare a photograph of the sky from 100,000 years ago with one from today, the differences would be striking. The stars would still be there, but their relative positions would be different. The familiar patterns would be stretched, rotated, or completely unrecognizable. So the Hunter, as a figure, is a temporary story written in moving points of light. Now, let us take a moment to think about what this means for the idea of cosmic time, because this phrase can sometimes feel distant or abstract. Cosmic time is not something separate from the time you experience. It is the same time, just measured on a different scale. Your day passes as the Earth rotates. Your year passes as the Earth orbits the Sun. But over those same days and years, the Sun is moving through the galaxy. The stars of Orion are moving through the galaxy. The galaxy itself is moving through the local group of galaxies. So your life is happening inside a much larger flow of motion. Every moment you experience is also a moment in the long, slow drift of stars. Now, let us imagine what it would be like to speed this process up, just in thought. Picture a time-lapse of the night sky, not over hours, but over millions of years. The stars would slide across the sky like slow-moving insects. Patterns would stretch, compress, and dissolve. New alignments would form. Old ones would fade. Orion's belt would bend. The shoulders would drift away. The Hunter would lose its shape. At the same time, new stars would appear as others disappear. Supernovae would flare and fade. Nebulae would brighten and then disperse. The sky would become a dynamic, changing landscape, not a static backdrop. This is what the sky really is. We just experience it in a very slow frame rate. Now, let us bring this back to the idea of size one more time, because the slow drift of stars adds a different kind of bigness to Orion. Orion is not just big in space, it is big in time. It is a region that exists across millions of years, evolving, changing, and eventually dissolving. So when you look at Orion, you're not just seeing a large region of the galaxy, you're seeing a phase in a long process. This can add a quiet sense of continuity to the view. The stars you see were born long before you existed. They will continue moving long after you're gone. The shape you recognize is a brief moment in a story that stretches far beyond any individual life. Now let us connect this back to something very simple and immediate. The next time you look up and find Orion, you might notice how steady it feels, how reliable its shape seems. You might think about how it rises and sets, how it returns each year in the same place in the sky. And then, quietly, you might remember that even as it feels steady, it is drifting. The stars are moving. The region is changing. The hunter is slowly becoming something else. That thought does not have to be heavy or dramatic. It can simply sit there, a gentle reminder that change is happening even when you cannot see it. Now let us take one more step forward in this journey, because the slow drift of stars is not the end of Orion's story. Beyond the movement of individual stars, there is the movement of the region as a whole, its path around the galaxy, its place in the larger structure of the Milky Way. And beyond that, there is the movement of the galaxy itself, its interactions with neighbouring galaxies, its place in the wider universe. After travelling outward through layers of distance, time and motion, it feels natural to let the focus soften and return to something familiar. Not in a way that closes the door on everything that has been explored, but in a way that lets all of it settle gently back into the simple act of looking up from where you are right now. The vastness of Orion, the depth of its neighbourhood, the slow drift of its stars across millions of years, all of it can fold quietly into a single moment beneath the night sky. You might be indoors as you listen, or perhaps imagining yourself outside, standing somewhere open, where the horizon stretches out in front of you. The air is still, or maybe there is a light breeze. The ground beneath your feet feels solid and dependable. Above you the sky opens into that familiar dark canvas where points of light begin to appear as your eyes adjust. Somewhere in that field of stars, Orion takes shape. At first it is not a hunter or a figure, it is just brightness and arrangement. A few points stand out more strongly than the others. 3 of them form a line. 2 of them sit apart, one with a warmer glow, one with a sharper, cooler light. And then, almost without effort, your mind connects the dots. The belt appears. The shoulders take their place. The feet find their position. The faint blur of the nebula settles beneath the line of 3 stars, like a quiet breath held in the background. In that moment, you are back on Earth, grounded in a human way of seeing, where the sky becomes a surface and the stars become a picture. What is different now is not what you see, but what you know is there. Behind the familiar outline lies a region of space that stretches across hundreds and thousands of light years. The warm star at the shoulder and the sharp blue star at the foot are not just markers in a shape. They are massive suns, each one pouring out energy on a scale that is difficult to compare to anything in everyday life. The belt is not a short line across the sky. It is a slanted bridge reaching deep into the galaxy, connecting stars that exist at very different distances from you. The faint nebula is not just a soft glow. It is a vast cloud of gas and dust, a place where new stars are forming, where future solar systems may be taking shape inside swirling disks of material. The entire region is not still. It is drifting, stretching, changing, carried along by the slow rotation of the Milky Way and the individual motions of its stars. And all of that is happening now, even as the light you see is a message from the past, arriving after centuries and millennia of travel. So when you stand beneath Orion, you're not just looking at a picture in the sky. You're standing at the edge of a layered volume of space and time, one that connects your present moment to events that happened long before you were born and to changes that will continue long after you're gone. This is a lot to hold in a single thought, and you do not have to hold it all at once. You can let it come and go, like the stars themselves, appearing and fading as your attention shifts. Perhaps you focus on something simple, like the steadiness of the belt. 3 points, evenly spaced, quietly reliable. Then, maybe you let your attention drift to the warm glow of Betelgeuse. You might remember that this star is so large that, if it were placed at the centre of our solar system, it would reach beyond the orbit of Mars. You might remember that it is nearing the end of its life, that one day it will explode in a brilliant supernova, changing the sky in a way that humans have never seen before. Then your eyes might move to Rigel, sharp and blue, shining with the power of tens of thousands of suns, marking what feels like the edge of the figure but is really just one bright point in a much wider, deeper region. You can move back and forth between these ideas, between the simple and the vast, without needing to resolve them into a single complete picture. This is one of the quiet strengths of the night sky. It does not demand that you understand everything it contains. It simply offers itself, layer by layer, at whatever depth you're ready to explore. Now let's take a moment to think about what it means to be here, on this planet, looking out into a region of space that is so large and so old. The Earth is about 4.5 billion years old. The Milky Way is more than 13 billion years old. The stars of Orion, as a group, are much younger, many of them only a few million years old. So when you look at Orion, you are looking at a relatively young part of the galaxy, a place where new stars are still being born, where the story is still actively unfolding. And you are doing this from a world that itself is part of that story, made of elements that were forged in stars that lived and died long before the sun ever formed. So there is a quiet connection between you and Orion that goes beyond light and distance. The atoms in your body and the atoms in those stars share a common origin in the life cycles of earlier generations of suns. This does not mean that you and Orion are the same thing. It simply means that you are part of the same larger process, one that stretches across the galaxy and across billions of years. You do not need to think about that in a grand or dramatic way. You can let it sit quietly in the background, like a soft, steady presence. Now let us bring this back to something very immediate again, because even as all of this vastness exists, your experience of it happens in a very small personal space. You might be sitting in a room, listening through headphones. You might be lying down, letting the words drift past as you imagine the sky above. You might be somewhere where you can actually see the stars, or somewhere where the sky is hidden behind clouds and city lights. In any of those places, Orion still exists. The region is still there, stretching across space, its stars still burning, its clouds still forming new suns. Your awareness of it does not change what it is, but it does change what it means to you. Perhaps it becomes a reminder of distance, of how far beyond everyday concerns the universe extends. Perhaps it becomes a reminder of time, of how long things last and how slowly they change. Or perhaps it simply becomes a familiar shape, something steady you can return to season after season, year after year. All of these ways of seeing can exist together. Now let us think about the idea of infinite for a moment, because it often comes up when we talk about the sky. The figure of Orion is not infinite. It has a size. It has boundaries, even if they are fuzzy and gradual rather than sharp. The region will not last forever. The stars will move. The clouds will disperse. The shape will change. And yet, when you stand beneath it, it can feel infinite, because your ability to explore it, to think about it, to imagine what lies behind it, does not really have a clear end. you can always take another step outward in scale. You can think about how Orion fits into the Milky Way. Then you can think about how the Milky Way fits into the local group of galaxies. Then you can think about how that group fits into larger structures, clusters and superclusters, and the vast web of matter that stretches across the observable universe. At each step, the previous one becomes smaller, not in a way that makes it less interesting, but in a way that places it within something even larger. So the figure in the sky becomes a doorway, a way of moving outward through layers of understanding and imagination. Now, let us return to the idea of drifting, because that word has been with us for a while. The stars of Orion are drifting. The region itself is drifting around the galaxy. The galaxy is drifting through space, interacting with other galaxies, moving within the larger structure of the universe. And you, in a much smaller and more immediate way, are drifting through your own time, moving from one moment to the next. These kinds of drifting are not the same, but they share a certain quality. They are slow, continuous, and often unnoticed while they are happening. You do not feel the Earth spinning beneath your feet. You do not feel the sun carrying you around the galaxy. You do not feel the galaxy moving through the cosmic web. And yet, all of that motion is real. In the same way, you might not feel the passage of time while you're listening, while your thoughts wander, while your breathing settles into a steady rhythm. But that movement is real too. So there is a kind of parallel between the slow drift of stars across cosmic time and the quiet flow of moments in your own experience. You do not need to draw a deep connection between them. You can simply notice that they both exist, each on its own scale. Now, let us bring this gently back to Orion one more time, because this is where all of these ideas converge into something you can actually look at. The next time you find the hunter in the sky, you might let your eyes move along the familiar lines, from the warm shoulder to the belt, from the belt to the sharp blue foot. As you do, you might remember that those points are not just lights on a surface. They are places in space, separated by hundreds and thousands of light years, connected by beams of light that have been travelling for centuries to reach you. You might remember that the faint blur beneath the belt is not just a smudge, but a region where stars are being born, where the future of the galaxy is quietly taking shape. You might remember that the entire pattern is temporary, that over millions of years it will stretch and change, eventually becoming something unrecognizable. And you might remember that even as all of that is true, the shape you see now is still yours, still part of your experience, still something you can return to whenever the sky's clear and the night is quiet. There is no need to rush through these thoughts. There is no need to hold on to them tightly. You can let them drift, just as the stars drift, just as the light drifts, just as time itself drifts from one moment to the next. Now, let us think about what it means to come back after a journey like this. Even if the journey has been entirely in thought, coming back does not mean leaving the vastness behind. It means carrying a small part of it with you, quietly, into whatever you do next. You might go to sleep. You might continue listening. You might step outside and actually look up at the sky. In any of those cases, Orion remains what it is, and your relationship to it remains something you can shape in your own way. Perhaps it becomes a place you visit in your imagination, a region you return to when you want to think about something larger than your immediate surroundings. Perhaps it becomes a simple comfort, a familiar pattern that reminds you of nights spent looking up, of seasons passing, of the steady rhythm of the year. Perhaps it becomes a question, an open-ended curiosity about what lies beyond what you can see and what you can know. All of those are valid ways of carrying this with you. Now let us allow the focus to soften once more, not to end, but to settle. The hunter remains in the sky, whether you're thinking about him or not. The stars continue to burn, the clouds continue to shift, the light continues to travel, and you remain here, in this moment, connected to all of that by nothing more than awareness and a beam of light that has crossed a vast distance to meet your eyes. There is no final conclusion to draw from that. There does not need to be. You can simply let the image of Orion, layered with all of this depth and motion, rest quietly in your mind. Because beyond the figure, beyond the region, beyond the galaxy, there is always more space, more time, more structure waiting to be explored. And even here, beneath a familiar shape in the sky, that sense of openness remains, gently inviting you to keep looking, keep wondering, and keep drifting, one small, steady moment at a time, into whatever part of the universe you choose to imagine next.